Okay, it's 12 p.m. in Chile, which makes 15 UTC. And I see we're over 210 participants on Zoom already, so I think we're ready to start. Welcome, everybody. My name is Alvaro Rivas. I am an ISO Alma Fellow in Chile. And it's my pleasure to welcome you all to the 5 years after HLTau, a new era in planet formation conference. Let me share my screen. So, yeah, we're super happy to have you all here. We are really looking forward to a full week of planet formation and protoplanetary science. But before we jump into that, we want to give you a few details about the conference and about the logistics. And we want to start by thanking all the people on these lists, the LOC and the SOC. They really helped putting this conference together, and we wouldn't be here today if it wasn't for their help. So thank you all very much. This conference has been on the making for over a year and a half now. It all started in April 2019 when there was an ISO call for workshops to be held this year. And we thought that it was a good opportunity to have a conference to talk about the different changes that the field had experienced in the last years. So we submitted a proposal in which we wrote 2020 will be the 5th anniversary of the publication of the groundbreaking ALMA image of HLTau, marking the beginning of a revolution in our understanding of planet formation. We proposed to hold a conference in the south of Chile in December 2020 to review the profound changes experienced by the field. A couple of months later, ISO came back to us and told us that this was a good idea and that they were going to fund the conference. When also NRAO, and in particular NGVLA, also joined as sponsors for the conference. And the original idea was to have something like 100, 120 participants. And the reason why we wanted it to be in the south of Chile, as many as you know, is that there's going to be a total solar eclipse in the south of Chile, in Pucón and Villarrica, next Monday. It's like 10-hour drive from Santiago. But unfortunately, 2020 had different plans for all of us. So we're not gonna be able to get all together and watch the eclipse, but we did not want all of you guys to miss the show. So we've been running some hydrodynamic simulations coupled with radiative transfer codes to bring you a state-of-the-art model of how the eclipse will look like. This is our best fit so far. We're kind of hoping that we did a mistake in the opacity value, but we'll see what happens next Monday. So yeah, by August this year, it was pretty obvious that we were not gonna have a physical conference, and we decided to move to an online format. And the response from the community has been great. It's been much better than we anticipated. As of now, we have 576 registered participants. This type of online conference allows people from all over the world to join, even people that may not have been able to attend otherwise. We've also received a lot of contributions. We have 131 contributed talks on the conference YouTube channel, which are already available, and 45 contributed posters also available on the Zenodo repository for the conference. So these are the asynchronous contributions to the conference, but we also have a live section in the conference, which we're starting right now. And that includes 12 invited review talks. We're gonna have 2 general discussions on Wednesday and Friday, including 25 panelists each. And at the end of today, tomorrow and Wednesday, we're gonna have short live presentations for 45 minutes by contributors who want to summarize their work. So as I said, all the contributed talks are already on the conference YouTube channel. But right now we're doing this live session on Zoom, but we're also streaming that on YouTube. So if you have to leave at some point, or if you're in a different time zone, this will stay on YouTube, and we will post this on YouTube as soon as we finish the live session, so that everyone can follow the conference and you can engage in asynchronous discussion too. We also have a Twitter account, so please feel free to follow us and use the hashtag HLTau2020 if you tweet about the conference. And last but not least, we want to emphasize that the conference has a code of conduct. It's on the website. We encourage you to go check it because any violations will result in banning from the conference. So please be respectful and professional at all times. And if you see any violation, feel free to report it to any of the LOC members or send us an email to the conference mailing list. And I think that's all I had. I'm going to hand it over to Enrique now, who will tell you more about the logistics. Thank you very much, and we hope you enjoy the conference.
Thank you, Albert. Yes, so as Albert said, I'm going to be talking a little bit about logistics now. So let me share my screen. There you go. So, yeah, as Albert, I think Albert mentioned, we're going to use Slack for all the offline discussions. You should have received the invitations. If you have not received an invitation, check your spam folder. If it's not there, send us an email and we'll resend it to you. Slack is basically just like a forum, a program to chat with people. The conversations can happen in different ways via public channels that these are like group conversations, large group conversations, anyone can join them. Not so private conversations, like direct conversations between two people or more. This is the screen of Slack. Those are here on the left. You have here, you're going to have all the list of the channels that you have already joined. If you click here on this plus sign, you can browse the channels and join any of the channels that you see. You can also type here in this search square, you can type here a search for a channel that you can then join, or you can type for your favorite colleague. And then if you click on it, you're going to start a direct conversation with that person. Here is just the number of people that are in that channel, just in case you're not sure whether that channel is going to reach everyone or not. And then you're going to see also these hashtags in the messages. These are links to other channels. If you click here, you're going to go to a different channel and you can join it. So by default, the channels that all of you are going to be in are these. There's one per topic covered by Review Talk, and this is the name format that we've chosen. These are channels that we're going to be using for general discussion about that particular topic, and also to follow up the questions of that you gave or you asked that speaker. There's also going to be 2 for general discussion sessions on Wednesday and Friday. And there's also these random and say hi and job opportunities channels. Additionally, there's a few other channels that you can join. There's one called Help Desk that is just, if you have an issue, let us know. And then there's one per contributor talk and poster with this format. You can find these listed in all the particular topics. You're gonna find a list at the beginning with all the different contributions. If you click on here, you'll go to the channel, you can join it, and you can start talking about that particular talk or poster with the presenter. You can also search for the last name of the presenter in the box, and then you're gonna see that channel as well. So this was Slack. As we've mentioned in our emails, we're gonna be using Slido for the Q&As. So you're gonna see that in Zoom right now, you don't have any Q&A window, you don't have any chat window. All the questions should be directed through Slido. So Slido is really easy to use. You just go to www.slido.com or slide.do, and then you see this web page. The first thing that you need to do is go here and enter the code for the conference, which is HLTau 2020. Not very complicated code. When you input the event code, then you're going to see this screen. You're going to be able to choose different rooms. The Q&A room is the one that we're going to be using for the Q&As of the speakers. There's also these 2 general discussion rooms that we're going to be using for Wednesday and Friday. They're open already because you can start sending any questions at any time throughout the week. So once you click on the room that you want to select, this is more or less the window that you'll see. You can change room anytime clicking here. Then you'll see a list of the questions that have already been asked, listed by order by the number of votes. You can vote your questions by clicking on the thumbs up. And then if you see a question that is grayed out like this means that this question, we've highlighted this question because this is the question that is being asked right now to the speaker. It's being answered right now by the speaker. And then you can also click here to type a question. And when you click there, you're going to see these 2 things here. You can ask questions anonymously, or you can also click here and add your name. Feel free to ask them anonymously, no problem. And then also you're going to have a limit of 160 characters. So your questions need to be short and specific. You can ask as many questions as you want, but keep in mind that questions are moderated, meaning that those questions that go against the code of conduct of the conference, that are not relevant for the current topic, that are repeated or have already been answered, those will be rejected. So that those questions will not appear in the list for all the attendees. And then the most voted unanswered questions that have not been answered during the talk, we'll gather them and we'll move them to Slack so that the discussion can go on there. So we'll also use Slido to ask polls. So whenever we activate a poll, the poll will show up to you automatically, but you can click here anytime to go back to the Q&A. About when you receive a poll, this is what you'll see. There's a question and there's the possible answers. Just clicking one, click send, and we'll show the results afterward. And finally, a little bit about the discussion sessions. The discussion sessions are on Wednesday for the topics covered by the review talks on Monday and Tuesday, and Friday for the rest of them. As Alvaro mentioned, the discussion will have around 25 panelists and 2 moderators. The attendees will not be able to talk during the discussions, but you can interact through Slido by sending questions and also by answering polls that we're going to be asking during the discussions. When you are within a discussion, you'll see that when you type a question, you can add a label. If you click on this button here, you can add a label. Basically, this is just to organize the questions on the different topics that will be covered during the general discussion sessions. And then once the discussions finishes, all the discussion will follow up via Slack in the 2 separate channels that we have for them. So this was everything that I had to say about logistics. Now we can get started with the main activities of the session. Today's chair will be Joan Ajita. So Joan, please take it away.
Thanks. Welcome, everyone. It's a pleasure to be with you today and wonderful to be able to come together during a worldwide pandemic to celebrate science and share the incredible advancements in our field. I want to thank the local organizing committee for their incredible effort to put together this all virtual conference for us. And as Enrique already said, I'm really looking forward to an exciting week, and I'm sure you are too. So without further ado, let's welcome Laura Perez, who will give us a look at how this revolution got going in her talk, HLTau, Before and After. And remember, as Enrique already advised, you can ask a question at any time in Slido during the talk. Take it away, Laura.
Thank you, Joan. And thank you again to the organizers of this conference and all the effort that you have put to make this happen with these almost 300 participants I see. So welcome everyone. And the goal of this talk is to sort of set the stage for this conference and show what was the status of the field right before the amazing ALMA images that were presented back 5-6 years ago to the community. And very briefly, I will discuss what the aftermath was, but really the entire conference is about the after, okay? And so the first question that one may ask here is, why do we focus on HLTau? There are so many other interesting targets, and why are we just naming a conference after this subject? And HLTau has it all in a way, and hopefully I can convey these during the conference. But something very basic is if you go to Simbad and put your favorite target, you can get a list of references, okay? And it's not complete. But for HLTau, if you do this, there are over 1,000 refereed publications. So this means people care in the community about this subject. From very, very early on, one of the prototypical objects when you talk about low mass is star formation and planet formation. And in particular, I also went to ADS and searched for those publications that had HLTau on the title. And there are over 90 refereed publications with HLTau on the title. And the winner with the most HLTau on publications is Luis Felipe Rodriguez from UNAM, who has 8 publications with HLTau on the title. And it became internet sensation with the release of these ALMA images. And I wanted to take you on sort of a walk of the evolution of the field as time went by. And so this talk will be structured in two parts. There will be a before section and then an after section. And we will begin with the most obvious, which is setting the stage. And young stellar objects like HLTau will form out of the material in molecular clouds that are across our galaxy. And this little video, as we zoom in into the torus star-forming regions, will show sort of the extreme or special environment where HLTau is in this molecular cloud, in this region, the L1551 region, and accompanied by several other objects, and having a little surprise at the center for us when we get there. Okay, and so to set the stage, let's talk for a second about our current view of the star formation process. And this is for low mass stars, where it begins with inside a molecular cloud, a core that overcomes its own gravity. And generally we're talking about, a parsec scale or so. And we call these objects prestellar core, where the protostar has not formed yet. Eventually, gravity overcomes, you're able to form a protostar, and because there is some angular momentum in the cloud, we expect that a disk-like structure should be formed. And so generally we refer to these objects where we have a protostar, where there is still a large envelope and perhaps a disk. We classify them between class 0 and class 1 objects. And now we have gone to smaller and smaller scales, now a few thousand to several thousand astronomical units. And we expect that this material will either be dissipated or will be incorporated into the disk and eventually reach the Titori star phase, where you have the pre-main sequence star, the protoplanetary disk surrounding the forming object, perhaps already planets, and we're talking now much smaller scales, let's say 100 to tens of AU, to eventually reach the end of the formation process, where we have this pre-main sequence star surrounded by perhaps the debris from the planet formation process, and hopefully a planetary system. And to study these different stages, we went to very early on to classifications through their SCD. And so from the cold black body at the beginning of the phase, where you're only tracing the main core, to now the radiation from the star, which is really overcome in excess by the infrared emission from the surrounding envelope and disk, to eventually a smaller excess of emission when we're talking about class 2 objects, to reach the final phase where the excess will be very small, and where we are in the debris disk phase. And during this conference, we will be talking about several of these phases, class 0 and class 1 objects discussed on day 5, chemistry, which is very important and I won't touch on right now, discussed on day 2, together with disk evolution and multiple systems, which are also critical aspects on the formation and evolution of these young stars. And today we will discuss sort of the end process. We will have a very nice review of Exoplanet by no other than Didier Queloz. And we will have, I'm sure, an excellent review on debris disk by our colleague Meredith Hughes. And from the SCD, we could already say plenty about disk structure. The observations that compose an SCD are generally unresolved and can tell you a lot about this irradiated from the central star, very full of dust disks, okay? And this is because there are gradients in temperature hotter closer in and colder farther out, that are radial and also vertical, that will result in a spectral energy distribution in excess of the stellar spectral energy distribution that allowed us to identify a lot of these objects. And we could say something about this structure also from looking at SED when we looked at these special objects that are generally classified as transition disks, where if you have lack of material very close to a star, then you lack this hot temperature material that would mainly radiate at near infrared wavelengths. And so you will see this drop, sometimes almost to the stellar SED, in the spectral energy distribution. And so even from SED studies, we could say things about what the disk structure was. And I wanted to show you the first long wavelength SED that I found for HLTau, where all of these points are way in excess of the expected stellar emission at the near infrared to far infrared frequencies. And the authors here say, well, to have this strong excess in this case, we must be looking at an edge-on circumstellar disk with a lot of visual extinction, okay? And back then, in particular for HLTau, to know that there was a disk was still uncertain. And multiple avenues pointed toward actually having a disk. And so let's review a few of them. First, there was direct near-infrared imaging, where scattered light was detected and supported the idea that there was dust in a disk that was producing this scattering, together with earlier polarization measurements that supported this sort of elongated disk hypothesis. Then it came near-infrared speckle interferometry, so observations that show that this region was resolved, and it had to be in an elongated, given the different orientations that were probed with interferometry, asymmetrically about the star, suggesting again that there was this disk of dust, which was what these near-infrared observations traced, and perhaps gas. And the earlier observations at millimeter wavelengths that were done on this object show two interesting things. Well, very deep observations of the dust continuum emission that reach this unresolved structure, and this velocity diagram, a position velocity diagram, sorry, showing that it was the very little measurements that they had, you can see 5 data points there, was consistent with some Keplerian rotation. That was later found to not be the case, okay? But in any case, all of these observations were sort of pointing towards the idea that this very young star had a disk. But then what was more certain was that this region, the HLTau region, had outflows, winds, and jets that were observed and studied over the years. And the origin of these wind and outflow components had to be related to the accretion disk, okay? And at the beginning, there were observations that showed these very extended wings. So there was high velocity molecular gas nearby HLTau and XCTau that had to be related with having powerful winds in these objects. And eventually, observations a few years later showed that in S2, there was this very collimated and strong jet emanating from HLTau. And this high degree of outflow activity was discovered back then. And it was found to be part of all these young stars that are in the L1551 region, okay? And finally, CO observations allowed us to finally understand that there was an outflow in CO. And so here you can see the jet in dark blue and this very asymmetric outflow observed around the HLTau star. And it was in this publication that it was shown that the Keplerian motions that were shown before were really just picking up the outflow, and they happened to be consistent with Keplerian. But with these new observations, they could exclude these purely Keplerian motions. And so the disk idea was still uncertain then. And as time went by, the observations of this outflow and these winds got much, much better. And so here we see a jump on 1 or 2 decades where we can see very clearly these highly collimated jets and the entire HLTau region. And with further observations, interferometric observations that trace the molecular gas of CO and near infrared imaging, it was found that the source had a bipolar outflow that you can trace in the very innermost regions with CO, with H2, I'm sorry, and this asymmetric outflow in CO later on. And observations then of the disk also improved, okay? And here I'm gonna focus on the long wavelength side of things, because HLTau became the favored interferometric target over the last 3 decades at long wavelengths. And so it's not surprising that we saw then HLTau becoming a favorite interferometric target for ALMA. And so here is, of course, not a complete gallery of all the HLTau imaging that was done at long wavelengths using all these existing arrays or precursors to now the ALMA array. And I wanted to focus, because you can see how as time went by, observations got better and better. And I want to focus in the 2 highest angular resolution imaging of HLTau right before ALMA. And this imaging was focusing on the disk. The 2 studies that I'm going to show were revealing very interesting features in all of these objects, in this particular object, sorry. And so first, although we don't mention it so much, the innermost gap in HLTau was detected back in 2009. So observations with the VLA array that reached 50 milliards second resolution, which is about a factor of 2 of the highest resolution we reached with ALMA at 7 millimeter, showed something. So in the background, you see the 1.3 centimeter observations of this disk. And in the contours is where you see the 7 millimeter observations. And of course, the problem was sensitivity. This was before the upgrade to the VLA that allowed to get really, really high sensitivity observations of these systems. And so what you see here is that there are some regions in the disk that appear to align in what we know now the disk orientation is. But back then, the disk orientation was still quite uncertain. A lot of people still thought that the disk was very edge on because of the lack of precise measurements. And so the authors here realized that if they do across what they thought was the edge-on region of the disk, which was not, happened to be the major axis of the disk, but at least perpendicular to the outflow, you could see that at least in one of the sides, there was a gap there. The disk shows a gap at a radius of 10 AU, probably related to a decrease of density in the disk, okay? And this coincides with the now known gap, innermost gap in the system. And on the other hand, the HLTau disk properties and geometry were finally revealed at high angular resolution by these observations by Kwon et al. Using the Karma array, now at about a factor of 2 higher angular resolution than the VLA observations at 1.3 millimeters. And here you see that they were really on the verge of discovering these gapped concentric rings and gaps that we now know exist not only in HLTau, but in a whole bunch of other disks. And the authors did a very nice job of modeling multi-wavelength images. They had more than one wavelength, but this is the highest resolution one. And showing something very interesting that the ALMA data were able to confirm later on. And is that although the SCD prefers a very thick disk, remember, from the SCD, we can say a lot about the structure of the disk, and having lots of excess at sort of mid to far infrared wavelength can be consistent with a very thick disk. But the millimeter wavelengths, the modeling that was performed, as it says here, prefers a thin disk. And the only way to reconcile it with the thick disk that was needed to produce the mid-infrared emission observed in the SCD of HLTau was that there was settlement of the large grains into the midplane, okay? And this is something that I will discuss in a few more slides that we now know. So there were similar images, okay? Maybe not as high angular resolution, but very similar for many other such disks. The imaging that was done for HLTau was really representative of what resolved imaging in the field was back then. And we could learn a ton from these surveys, either for disks with resolved cavities or full disks or a combination of those. And I take a quote from Andrei Sela's paper because this is what happened. The advent of ALMA will enable us to expand the number of spatially resolved disks by a large factor and have a much complete view of the structures in young disks. And so ALMA came along, okay? And at the beginning, it was low resolution imaging, which still provide a ton of new information, from detailed single studies of specific objects to very large surveys. And as you will discuss on day 2 on demographics by Ilari Pascucci, there will be we know that thanks to a sensitivity, we can go down to very low disk masses and hope to have complete disk samples to study really the material available for planet formation for a large sample of disk, not just the special ones like HLTau. And I wanted to show and give this idea of the true improvement that then the high angular resolution was going to bring. And so here is a diagram of our own solar system scales, okay? And here is the average resolution of all these large surveys and most of the imaging done before ALMA. On average, you could get a super-second resolution, which at 140 parsecs becomes this large beam. So you're really encompassing a lot of the scales in the solar system in one go. And the highest angular resolution that I was discussing before for HLTau was just a fraction, it's still a fraction of an arc second, 130 milliarc seconds, which corresponds to this little circle here at 140 parsecs. That is the best resolution before ALMA, and this is really what we now are used to call low resolution imaging that ALMA can routinely deliver. And the highest angular resolution, or the ALMA long baselines on average can produce, they can go down to this 25 milliarc second beam, although depending on frequency, they could do even better, which corresponds to this little circle there. So you're really probing spatial scales that are important. You're resolving these scales when you go to the long baselines of ALMA. And so this is why this was so critical and so important to do. And the promise of ALMA had to be fulfilled. The long baselines had to be tested. And for this, ALMA created a long baseline campaign that ran for a few months at the end of 2014, where ALMA scientists working in Chile at the JAO, joined by ALMA scientists that were working in the different nodes all over the world, but plus international experts joined together to try to make the promise of ALMA happen. And one of the first duties that the long baseline campaign had was to select interesting targets to test this new capability of the array. And as you saw in the handbook of the conference, an email thread by the JAO, the Joint ALMA Observatory, had HLTau suggested as one of the science verification target for long baselines. The suggestion came from Neil Phillips, and as Antonio Ales said, it was the easiest proposal ever accepted. And the one quick story I want to say is that when I joined the ALMA long baseline campaign, and one of my tasks was to find some backup targets for the long baseline campaign instead of HLTau, I remember thinking, why are we doing HLTau? There is the imaging from Karma that showed that this is smooth. And so we might resolve out everything and end up with a crappy image. And so I suggested a long laundry list of more compact disks that were still very bright and fulfill all the requirements regarding spectral line imaging, et cetera, et cetera. But I'm happy I was wrong. And I'm happy that we end up having HLTau as the first circumstellar disk to be observed at high angular resolution. And to show you the amazingness of this, I have a picture from the long baseline campaign here. And you can see this is the Changnator Plateau. It's not so flat. And you can see the main array here, and these little pixel-sized white dots are antennas in some of the long baseline arms. And you can see the road continues, so you can have more of those antennas there. And the promise of ALMA was already in the scientific specifications and requirement back in 2006, where if you read it carefully, you can find that one of the goals was the ability to image and detect the tidal gaps created by planets undergoing formation in disks. So we at least detected some gaps, okay? And this is now routinely done by the observatory. And so the promise of ALMA, I believe, was fulfilled. The concentric rings and gaps in the HLTau ring, in the HLTau disk at sub-millimeter wavelengths were finally revealed after a very successful ALMA long baseline campaign. And I think everyone had a reaction to this image, but the thing that has made me the most happy is to go to astronomy apartments where I go give a talk or meet some colleagues and see this image printed in the poster board or in some random office. It really created such an amazing display of wow. that so many people wanted to sort of join in the excitement, and they had these images plastered in their office, even if they didn't work on young stellar objects or they didn't work with ALMA. It was very nice to see, to witness. So here's the angular resolution. We were talking about a few astronomical units at 1.3 millimeters, and you can see that this was really a team effort from the technical side, where they had everything in place to make this happen, to the astronomers working at the telescope, to really everyone at the ALMA JAO, okay? And I wanted to quote, just to have a quote from this paper, that these continuum images have high angular resolution that reveal astonishing level of detail with a pattern of bright and dark rings observed at all wavelengths, because this was a test of several different bands from ALMA. And so now that we saw the image and we talked about the excitement we felt as astronomers, this was really something that was felt worldwide. And so the BBC, the New York Times, and several other international publications that are very exciting really showcase and had this orange image plastered, just as you see it plastered over astronomers' offices in the world. And so here we wanted to have a poll because we would like to hear from you. In one word, what was your reaction when you first saw this HLTau image? So you can go to Slido and you can enter the HLTau 2020 code and just tell us in one word. And at the end of the talk, we will just share the answers with you, okay? So what was after? So really the goal of this conference is to discuss all of the aftermath from this HLTau image. And here I just have a laundry list of all the different things that have changed over the past few years and that we will be discussing at this conference. And I wanted to say that there's no time for me to discuss any of these in a lot of detail. So I will briefly discuss some of the ALMA partnership results and then focus on the first few items there related to the origins of substructures, solids and their evolution. How do we detect the young planets if they are there? And disk substructure. So from ALMA Partnership et al. 2015, we were able to also showcase crucial ALMA capabilities. Spectral line imaging is crucial now to do anything from kinematics, chemistry, and really understand from the large scale to small scales what is happening in young stellar objects. And what we show there was that there was this very complex outflow in the HLTau region where you don't see it to be in the blue sheet side very symmetric at all. We were able to do multi-wavelength high resolution imaging down to few astronomical units, which also allow us to measure spectral indices, for example. And when we analyze some of the concentric dark gaps and bright rings in the disk and measure their intensity variations in the spectral index and the brightness temperature of these features, we realize that the radial structure we see, which is correlated high spectral index with low brightness temperature in the dark rings, has to be a result of the lower optical depth that we see in these regions, okay? And so these regions are regions of where there is less dust. It was very, very exciting to work with this large number of people to get these results out to the community. But let's talk about the question that everyone had in their mind right after they saw the image is, what is going on? What may cause these concentric rings and gaps? And you all know you have a favorite answer, and you will be able to tell us what your favorite answer is in another poll during the coffee break, I think. But just to show one of the possibilities, right after the HLTau images came along, there were SPH simulations with pre-embedded planets in the HLTau disk that show that a model with these parameters was able to reproduce all of these concentric ring features and supports the conclusion that maybe planets are responsible in this case. There have been several other simulations done afterwards. I just wanted to highlight the first one that came after. And of course, there are several other different flavors for the origins of these rings and gaps due to secular gravitational instabilities or MHD instabilities, viscous driven by dust instabilities, and sintering, which is related to ice lines and so on. And so there are many other flavors, and there are several talks in this conference that you can go and watch to deal with the cause of these rings. And something that has been critical after to infer physical properties across the entire disk has been multi-wavelength imaging. And you will see there will be 2 days talking about dust and planetary formation and talking about polarization and magnetic fields that really require some of these observations. And I will just briefly discuss 2 results, imaging done then with very high sensitivity with the VLA, allowed a team of people to infer the radial distribution of solids in the HLTau disk and really constrain the differences between the dust properties in the dark ring and the bright rings and the dark gaps. Where again, the dark rings are of low density and have small dust. And a very interesting result as well was to look at these images and to do relative transfer modeling and show that there is vertical particle settling. So the particles, the large particles must have settled in the HLTau disk, because when you don't add settling as, oh, I'm sorry, and here it should have said Pinte et al. I apologize for this mistake. It's not Carrasco Gonzalez, it's Pinte et al. 2019. Apologies, Christoph. But without settling, you are not able to azimuthally infer the presence of the gap at all azimuthal angles. So you really need settling and a disk that is geometrically thin. And of course, the next question that one may ask after seeing this is, well, are the substructures observed in this one object actually common? And so there have been further high angular resolution imaging that has revealed a very large diversity of features in the solid distribution of the disk, in the distribution of solids in the disk. And you can see some examples here. In this conference, there will be very, very many talks recorded that you can watch, dealing with detailed studies on single objects to these large observations. And further, substructures in the gas. So I urge you to all go and join these talks. Now, to sort of get to the end of this, well, if rings are common, then where are the protoplanets? So if rings, as some of the substructure studies have shown, appear to be common, then these protoplanets have to be there. And the search for these either stellar or planetary mass companions is currently ongoing. And the first one, I'm sorry, and you will hear about these surges on day 4 when we have the young exoplanet talks, and of course the kinematics on disks as well. And so the first one of these hunts for young planets was done in the HLTau right after the HLTau observations came out, showing that at least in the gaps observed here, there are no really massive planets. And that's okay. It's consistent with the predictions from hydrodynamic simulations. The planets don't need to be really massive to carve the gaps observed in HLTau. There have been other works hunting for planets in gaps as well, but now using kinematics. And now I have the reference correct, Pint et al. 2019, showing that at the location of a gap, there is this kink in velocity, this change from the pattern that should not be there unless there is something really massive driving this change that is unseen at the current sensitivities for instruments like a sphere, for example. And I wanted to just highlight one case where maybe we're on the right direction, I don't know. And it's the work by my graduate student, Sebastián Jorquera, where he has been hunting for planets inside the gaps of a sample of protoplanetary disks. And in the very deep gap of Elias 24, we find this point source, which is located right at the deepest region of the gap. And if one makes the assumption that it's a planetary companion, it will have a mass that will go from half a Jupiter mass to 5 Jupiter masses. And this mass range is consistent with the hydrodynamic simulations that explain the presence of this gap and this bright ring outside. But we're still calling it a candidate because honestly, this needs further confirmation because the probability that Sebastián calculated to find this planet is still low at this very small inner working angle. So I'm gonna just stop here and tell you, we will be talking in this conference about many more results related to demographics, earlier disks in younger objects, chemistry, disk evolution, multiple system polarizations and dynamics throughout this conference. And so I just want to give a few concluding remarks and say this iconic HLTau image has really made a revolution and brought forward a new era in planet formation. And this happened together with new developments in exoplanet science that we will hear about in the next talk. New and upcoming facilities will really open also new windows to this, like for example, JWST, and of course, further theoretical progress that is happening now in the field. So I leave you with, there is so much to do. We can have a lot of fun. And thank you again for listening and for the opportunity to tell you this nice story. Thank you.
Thank you so much, Laura. And for anyone who can unmute, let's give Laura a hand. Terrific talk. So let's go to the questions. And I see that there are a number of questions in Slido. Oh, there's also an answer to the poll. So there we go.
Wow. Nice simulation. I like that.
So just connecting up with.
Sorry?
Go ahead.
I have to say that when I first saw the first execution, so it wasn't the full image, it was just the first hour or so on source in the first band that we tested. And there was already the gap there. And I thought, no, there has to be something wrong. So I think this wow plus no certainly showcases what many of us felt there. So this is really nice to have and to just bring everyone together.
So true.
Good.
That was, in fact, one of the questions was, what was your reaction? So I think we've answered that one. One question is, are we at the limit of high angular resolution images? Can future telescopes significantly improve the high angular resolution sensitivity observations?
So this is a very good question. In terms of ALMA, there are certain bands, so high frequency bands, which we have not gone for yet in high angular resolution imaging. But the problem is these are the higher frequency bands or shorter wavelengths, which will suffer much more from high optical depths than even the current ALMA bands that we have tested. And so future facilities that will be amazing for this are some of the ideas of a next generation BLA. So you really go to the long wavelengths you need to probe the lower optical depth of material that really can show you at the innermost regions of the disk, terrestrial planet formation. zones, but also to stop looking at this beast, okay? All the figures I show here are the very special bright objects, and it will be very nice to really reach the high angular resolution to see planet formation in action in the more normal disks that are more compact and that require high angular resolution.
Thank you. A question that many people want to know the answer to is, what is the explanation for why people originally thought the disk was edge-on based on its SED?
I put it, through reading the literature, I have to say people could not imagine this high extinction in the very early works and this very high excess of emission. And so they could only imagine that it had to be edged on, so that you really could explain those current observations. But it was the new set of observations from the millimeter wave interferometers that really showed at the very early stages that maybe it was not so edge on, and it had some less than 90 inclination. And it was shown beautifully in the very high angular resolution imaging that was done with Karma, for example.
It certainly had the object has certainly had a long and varied history in our interpretation of what we're seeing.
Yes.
Another question is, what do you think will be the next HLTau image kind of result? I guess something that also inspires wow.
Well, direct imaging of planets, of forming planets, will certainly be the next wow thing. And there are instruments that could provide this in the very short-term future when we think about JWST, for example. And it will image things far away, far away from the innermost disk regions, but I think it will still be exciting. There will be also instruments to do this with the extreme telescopes like the GMT or the ELT. And so I think there will certainly be a lot of excitement from direct imaging of these forming planets there.
And maybe some of those wow observations will be reported at this very conference. So I'm really excited about that.
Yeah.
Let's see, we have a couple more questions. Could well-resolved class 0 disks also be the next resolution revolution?
Certainly, I think this is setting the time scale for planet formation will be important, and understanding, of course, what causes these features as well. But if we start seeing these features in earlier and earlier disk, I think this will also be a wow moment for the field. And as thinking that HLTau was edge on looks like a strange thing to think, well, maybe we will in the future be able to explain or discover if planet formation timescale is actually much shorter than we generally think of. And so I think these new observations that are coming along will also be critical to understand if class 1 disks, for example, already show these features and even earlier on. And there are some talks at this conference. Dominique Segura Cox has one, for example, showing one of these disks with all these features already, but much earlier on. And remember, HLTau is young. I didn't discuss this. Again, there is never enough time. But HLTau is already a sort of in-betweener. It's not your fully normal class 2 object. It's younger from all we know, and shows evidence of youth. And so this was also, I think, very surprising to the field to see it already in young objects. And there are several studies now trying to go to the earlier and earlier phases. And I find this also super, super exciting.
Definitely. So let's see, we have a couple questions that are about the, what are some of the future kinds of observations that could be made? One is, oh, some of our questions are disappearing. One is whether there's a technical improvement planned for ALMA that would make it possible to match the very high dust resolution, but with gas observations.
So there are improvements in the sensitivity of ALMA to try to go exactly at that, at improving the spectral line sensitivities. But we're still a few years off from that. But this is, I think, where the current improvements need to focus. Imaging at high angular resolution with more sensitivity of lines will certainly also bring a lot of new results to the field. And some of those are already happening. There are some high angular resolution observations related to chemistry. There's a large program, for example, where already many new results are coming. And something exciting is that spectral line imaging can also tell you something about the presence of these planets, because you can study the kinematics of the disk. And so pushing this line can really open several avenues, not only just chemistry, for example.
And one final question, since you gave us such a wonderful overview of the history of the field and observations of HLTau, do you think that it is some kind of special touchstone for our understanding of disks, or would the development of this field have been very different if ALMA had decided to go with to observe a different disk as its first high angular resolution observation?
This is a question that keeps me up at night because I had really in my mind this idea that HLTau was not the way to go because it was smooth. We will resolve out everything. And my favorite target was actually AS209. That was the one that I thought, okay, it's very compact, very face on. It will be beautiful. Spectral line imaging will be beautiful, et cetera, but it wasn't meant to be. And I wonder, because the structure is very different. There's a very compact disk and the very narrow rings far out. If we will be, developing different ideas from having to look at that instead of HLTau.
Thanks so much, Laura, for a fantastic hour and introduction to the conference. And I think that really sets the stage for our next speaker, who will take us to the endpoint of planet formation, to the planets themselves, and a look at their demographics. So let's welcome Didier Queloz, who will tell us about exoplanet demographics and architectures. Take it away, Didier.
Thank you very much. So I have decided to express my talk in a more cool way by mentioning we are living a time of revolution. So I think it's an exoplanet revolution I will be talking about. Let me just share my slide. So give me 1 minute here. Share screen, here we are, Microsoft share. And if I do that, yes, that's what it is. Do you see it?
Beautiful, thank you.
Thank you. Thank you for these kind invitations. I really do regret not going to Chile because you know how much I like going to Chile. I must have spent at least more than 1 year in Chile with all my different instruments I've built there, installed in different places. So I will be trying to kickstart this meeting by giving you a little bit of an overview of what I think is relevant, and relevant in the sense that what is the connections to the formation mechanism, the origin of planet, which is essentially what this conference is about. But I will also mention some element that is a lot in the press, which is related of the relevance of these planets in the habitable zone and the question of the looking for life. It's quite, in the news, and there is the Martian missions, a lot of stuff here. So I felt that when we talk about exoplanet, we have to try to address this question as well, and I want to give you what's going on to my understanding. Okay, let's kickstart with the reason why I believe it's a revolution. Is when you think about the field in astrophysics that has grown so tremendously, I can only think another one, which is at the time when people started to try to get to the origin of the universe. And in 25 years, they complete revolution the way we see our place in the universe. And I think what we have done in the last 25 years on a more smaller scale, but a profound implication as well, is found so many exoplanets. And it's to give you a snapshot what has happened since 95. And the reason why I mentioned this is essentially two techniques which early on was not the most promising one. They were not identified as the big techniques that should be used for searching for planets, but turn out to be tremendously efficient. And one of them is the one we've been using to find the first one, which is the Doppler velocity, radial velocity, or precise radial velocity. And the other one is a transit with emblematic transit mission like Kepler that has completely changed the game. So this is where we are. So it's pretty clear that there are really a zillions of exoplanets. It's no problem about that. But what does it mean? And what does it mean for the understanding we have of our own solar system? And what is quite amazing about this is while we've learned a lot about exoplanet diversity, we're still pretty much at the same situation we are to learn about the solar systems. And you will see why we're not at the end of the game here. And I think the study of the very early stage turned out to be very critical and certainly very exciting with all these new developments and the kind of topic of the conference here. So the other point I like to make, let me just remove this. Is whatever you do, whatever you want to put that aside, you can't. We all are absolutely focused by the planet of the solar system. And there is a good reason for that, because we will never, ever reach the level of detail that we have of these systems. So these are our reference points. Whether you like it or not, we always talk about Jupiter, Neptune, Uranus, Earth, Venus, and Mars. When we don't know, we're talking about, we add superlative like super or mini or large, but still we still have this in mind. And that is something which is, I think, good to keep in mind because it has an impact on the way we understand the diversity of exoplanets. Well, let's open then the planet, and we know that these planets, we have a kind of fair understanding of what is inside, but still, there is still people debating whether there is a core in Jupiter. And it's a very valid question because there has been a couple of probes and there's still a lot of questions about there is a core. So we are assembling a whole theory for exoplanet while we're still debating on the very critical element of the formation of Jupiter, which is the nature of the core into Jupiter. But the rest, we pretty much agree. We're talking about hydrogen and helium, same than the sun. When you go to Uranus and Neptune, we have a fair understanding what's going on these planets, that must say, but we have not really studied them in great detail about this. And we still use this reference, Uranus and Neptune, certainly Neptune, when we're talking about planet which is smaller than Jupiter and Saturn. It's fair to keep in mind they essentially have the same structure than Jupiter. The main difference here is they have essentially far less hydrogen and helium, and this is related. One of the ingredients that we use to understand the formation process of these systems. And then we're left with the rest of the solar system, which I think is as critical as the nature of the planet, and we should really keep that in mind. There is really a lot of very fascinating studies about the detailed structure of the system. It may be a little bit old-fashioned when you talk about cometary bodies, because it seems to be an old-fashioned science, and when astronomers were looking for comets. But you've seen a lot of excitement that there are these days, especially with the return right now of the Japanese probe, and there will be even more excitement by returning ingredients from other probes and from other planets. And the reason why, because whatever you like it or not, this is the imprint of the formation of the system. So you can talk about whatever you like about disk, at some point you have to come up to that, which is a real object of different form, different nature, a different orbit. Well, this is what we have on the solar system, and it's extremely rich. And there is a lot of knowledge that you can withdraw for that tell you a pretty good story about the origin of the nature of the planet, of the system. Well, the good news for you guys doing disk, if you look at the scale, when you just superimpose the famous beast that is the topic of this conference, HLTau, you will see that you're not very far from matching the structure of the planet, of the solar system planet. So that's a good start. And certainly you can imagine that at some point there is something going on in that disk that should lead to the structure that you had just here on the solar system. So that's good news for you. So there is a connection between the two. But the bad news is it's not exactly working, I think, the way we see it, because I just want to remind you, this is just a tiny fraction of the disk you're talking about here. It's just a solid particle you're seeing here on the thermal emissions. So I like to see that in a different perspective and to bring another very famous object, which is that one that everybody would have recognized, Beta Pictoris. And the reason why I want to show this one is about the same scale, a bit bigger. So I have superimposed two pictures. One is pretty old, which is the famous HST picture, which is a reflected light. It's essentially the visible light from all the tiny particles you have, very thin disk, you have it. On the other one, you have the ALMA gas, CO2 measurements in Beta Pict. And the reason why I show these pictures, I think this is really the essence of the problem we are in a disk, is the disk challenges is you have two different materials you have to deal with. You have the gas and you have the material, solid materials. And essentially you don't see it the same way depending how you want to observe it. And that opens a lot of interesting debates of the nature and the structure of the disk. But the worst of it, they are not a clear cut between the two, because you can move from a gas to a solid particle and you can move from a solid particle to a gas. It just depends on the nature of the gas you're talking about and the temperature. The very famous example is water. So depending on where you sit, you end up with a gas or you end up with a solid. And this very strict definition of the solid particle that essentially follow the gravity in that case, or the gas that is much more related, they have to deal with the pressure, and then you have a different pattern that have to obey, makes the whole complexity in the formation of the planet. And this is essentially the rationale to explain the planet of the solar system, and that's a big challenge to understand all this exoplanet that has been found. And who could you fit in this with a very incomplete picture you have into the disk? And I think we're not yet at the end of it. The reason why is the main conclusion from that is, assuming you need a lot of solid particle to build the core of the planet, you only find the solid particle where there is a lot of material that is solid form, which is essentially beyond the ice line. And this is why you have the Jupiter planets there. Everybody is happy with that. But the problem is, as you know, most of the planets we have found, they're not there. At least we have found a massive amount of planets and a different location. So I would like to open this chapter right now in a single diagram that is an absolute overview of what we know about exoplanets with 3 physical parameters, just 3. It's the period of the systems, the mass of the planet, and the radius of the planet. Well, I trick a bit the mass here because I assume that the sin I in case of radial velocity planet is 1. So you can change a little bit if you want. But globally, given the scale and the lob scale we're talking about, it's not going to change anything. The color here is depending if the planet has been found by transit. The blue, you have guessed, is the transit. The red is the radial velocity. Some of them have both. I come back on that later. But the point of this diagram is to give you a snapshot of what we know in terms of exoplanets. So we all acknowledge 3 different regime, or call it population. I don't really like the term populations, but certainly 3 groups of planet. The first one, which is the one that kickstarted the show, which is the hot Jupiters, very, very extreme Jupiter object. absolutely impossible object. It took 4 years for the community to accept that they would exist. It was quite of a difficult time, I must confess to you, from 95 to 99, until we finally had an obvious transit of one of them. And then that was the end of the game. And then clearly they would exist. The problem of this planet is they're just not supposed to exist at all for the reason I mentioned before. So we have quite a lot of them seen by transit and by radial velocity. And the good news of this object is they're very, very easy to transit. So that is a gift of nature, is the fact we had kind of detected this planet, opened the prospect for people to look for transiting planet. Well, the good news of this is transit has been very lucky. When you think about the Kepler missions, if you remove all the planet on short period, you end up with almost nothing. So Kepler would have been an absolute catastrophe without this extremely rich world that nobody had guessed of short period planets. So you have this kind of group of planets here that we call a kind of mini Neptunes or super Earth that are ranging a distance from less than a day, and some of them to a couple of weeks. And this is essentially a kind of counterpart of the hot Jupiter, in a sense that they have no counterpart in the solar system at all. They just have the Earth here to just help you to visualize. And they were not predicted at all by theory. Now, we still have the third group, which is more like what we would expect, at least in a sense that they are a giant planet. Transit is very poorly efficient for that because just the likelihood to find a transit, but the radial velocity is much better. That's why you have all this red object there. And you do have a significant amount of these systems. A little bit of a trick here. I missed a fourth dimension, which is the eccentricity of the orbit. And it turns out that a lot of them are quite eccentric, which is not exactly the kind of system you would expect to be like the solar system. So they are clearly Jupiter at long distance, but they are eccentric. So we have certainly to one day or another, we will have to understand that. I'm missing the direct imaging planet because they will be even further out in terms of distance here. There's very few, and I only got the main component. Essentially, the field of exoplanet, what we have learned is essentially comes from these two techniques, the transit and the radial velocity. For now, things are going to change in the future with the Gaia release sooner or later. And then there will be progress in direct detections and direct imaging for sure, and that they will come closer and closer to the radial velocity long period planet. But so far, and for the next 5-10 years, it's what we have right now to deal with. So what is fascinating here in these different categories is to see that when you compare with the solar system planet, they are essentially far away from what you would expect, and there are plenty of planets between the planet you would expect in the solar system. So this is the whole point I was making early on by saying you guys have a lot of this to deal with, but there's still a long way to go to explain how you end up this way, because essentially the disk would match pretty much what you expect in the solar system and how you end up like that. Things become even worse when you put numbers there and you try to get some occurrence of these different categories of planet. There is a really very let's say intense literature on that. So I've tried to capture the kind of range that people are talking about, but this is about the number that people are dealing with. So everybody agreed that the hot Jupiter are kind of a marginal set of planets, depending of different criteria, the kind of stars you're dealing with, and also the amount of metallic element you have in the atmosphere of the star. You end up with 1 to 5% of chance to pick of hot Jupiter on a star. So if you have 100 stars, we had 130, 128, I think, to start the survey in the 90s. So you expect 1 or 2, which is exactly what has happened actually at that time. So there is a small chance you will get it. The good news is they are very easy to pick up from the ground, and we have all these massive WASP discoveries and HAT discoveries, which is ground-based surveys that looked pretty much the whole sky and about this kind of object, at least down to the magnitude 12, 13th. Now, we have an interesting range of Jupiter, classic Jupiter, if you want, between 10 to 50%. The reason why the range is so wide is because nobody agrees exactly what is the end of it. So depending how you want to define the upper range of the mass of this object, you clearly see that it goes pretty high here. And there is, at some point, you will be eating the brown dwarf regime that you can argue endlessly whether it's a brown dwarf or the planet. I don't want to enter that game here, but depending on you go up, you can add quite a lot some. And then if you go farther away, due to the incompleteness, and then the range of how much you may be missing here can increase quite a lot. So I'm really looking forward, Gaia, here to tell us a bit more about the story here. And I expect this range to get clarified. But there is a good chance that a star will end up with a Jupiter, which is good news because that's exactly where you would expect them to be. You just have left to explain why most of them are eccentric, because it's not exactly what you expect from the formation mechanism, at least if you don't have a massive mechanism that change dramatically the angular momentum and the energy of the system. And then we have these amazing populations of, let's call them mini Neptunes and super Earth here. That is more than 50% of the star have such object. And actually, when you find out, you realize that there are more than one actually. So the chance to have more than one on the star is even higher. So frankly, I must admit, this is the gift. Because without this planet, I don't think there will be, I've seen 350 people attending these conferences. So the reason why we have so many people in this field is because of that. Because there are a population of planets that nobody had imagined they would exist before. And this is a fascinating population because we are here experiencing a range that is absolutely awkward. We are going down to object which is clearly less than the mass on the sides of the Earth, up to object into a regime that is beyond Uranus and Neptune, a regime which you don't really expect much of the planet because it's supposed to be an exponential growth, accretion growth of the gas at that point from the disk. So of course the location is absolutely awkward because if you imagine that most of them are born with a core outside, you have to be a pretty good efficient mechanism that is bringing this object in. And if this mechanism is so efficient, you should see something in the disk. So I really encourage you to have a look at this. Of course, this is challenging because talking about object 1AU, it means essentially talking about a few pixels on the image of HLTau that I was displaying before. So essentially, most of the planets we're finding are within the few pixels of your images, while at the same time, the origin of this planet may be indeed from the outskirts. So this is really a very fascinating element here, and studying the formation mechanism through time may be a way to understand this better. But even more fascinating is to look a bit more detail what we're talking about in terms of structure of this object. So before going that, I just want to spend a little bit of time to go through the explanation why we are so bad at finding planet in this regime here and then at that regime here. Well, first, transiting object can detect a planet like the Earth. It's pretty clear, especially if it's in short period. Well, the reason why is very simple. It's called signal to noise ratios. When you have a system which transit 20 or 30 times, you increase the signal to noise of ratio of square root of 30, and then anything that would be very tiny would just be enhanced. So the fact that you detect small planet, because they have a lot of transit. So what is challenging with the transit is the fact this is a very rare event, and when you have 2 or 3 transit, you're left over to only the big ones, and that is why you have no discovery of Earth-size transiting planet in 1AU, and it will remain quite a lot of time like that because it requires a lot of telescope time and many transit to do that. While radial velocity is a bit better on that because you don't need to rely on a very short-lived event where most of the time nothing is happening, but in radial velocity always something is happening, but too much. Because what you have here is the activity of a star. In that case, is the activity of the sun observed with the radial velocity spectrograph. In that case, it's HARPS North. It's fully published when you observe the sun as a star. And the scale here, it's kilometers. So you see typically the activity of the sun. You see the rotation pattern of the sun within the rotation period of the sun. And it's typically of the order 1 meter. So if you get a good machine, you see that pretty much, and you can understand the challenges that it is to find small planet in that structure, which is the intrinsic structure of a solar type star, which by the way is not very active because the sun is not an extremely active star. But in terms of discovering a small planet, the sun is too active too much, way too much active, until you find a way to deal with this kind of noise. So this is what the kind of signal that people are dealing with to detect object is 1 meter. So essentially all the planets have roughly 1 meter amplitudes. Depending of the period and depending of the mass of the star, you end up with a kind of Earth mass in some case. And of course, if you move to 1 AU, you have to decrease this amplitude regime much smaller. That will end up something like that. And this is clearly beyond now the current strategy of most of the surveys, because to end up finding objects like that, you need a complete new way to approach the problem, which is essentially observe an extremely intensive way stars for a very long time. And when I say long time, is more than 1 or 2 years clearly here. So this is not something which is being done, but there's a couple of experiments which is moving into this direction. So progress being made, but it will take a long time until we have filled the gap. In the meantime, we have plenty enough to deal with, because formally there is a fantastic astrophysical content in this kind of diagram. When you combine the mass and the size of the planet, keeping in mind that most of these planets are very close to the star, so most of them are quite hot. So you're not really dealing with planets exactly like the solar systems. But as I said before, whatever you like it enough, we're all biased because we know quite well the planet of the solar system. So we're still using this planet as a reference, and that's what I've been doing here. So this is all the planet with the mass and the size, with the error bar being measured here. And what you do see is the hot Jupiter, pretty clear. They're known to be inflated. Frankly, we don't know why. And there's a couple of ideas how it is inflated, but there is not a clear-cut explanation why. So it is inflated. They are very hot, so at least they are different from Jupiter, but still we don't have a proper mechanism to explain exactly, to predict. I think not a mechanism that everybody would absolutely agree on, but still kind of following the kind of a regime that we would qualify as Jupiter-like system. So if you take Jupiter and Jupiter structure and you change a bit the mass, assuming to keep the equation always the same, so you scale down Jupiter. Well, you don't change the size of the core. You just change the envelope and all the massive amount of gas you have around. And by doing that, you will follow the kind of gray hatchet curve here. You will meet Saturn along the way. Saturn is essentially similar to Jupiter in terms of structure. The core is clearly measured in case of Saturn. So the core may be a bit bigger, but again, it's not relevant for that kind of density diagram. And you can keep going down and keep going down, and you still find objects that are within this regime until I stop here, because this is the mass of Neptune. So Neptune is clearly denser than Jupiter and Saturn, and that's understood because the ratio of more heavy gas compared to the oxygen is higher. So you have much more heavy gases. You have less oxygen and helium. Sorry, that's hydrogen. Sorry, hydrogen and helium in this planet in Neptune's. This is why it's denser. This is why it disconnects from the density you get from Jupiter and Saturn, which is mostly dominated by hydrogen and helium. Now, to help to visualize what we're talking about, I added up one of these hypothetical density diagram when you assume it's full of water. So a water-based planet, 100% water-based, is just not realistic, but it tells you a little bit where you sit compared to Neptune's and compared to Jupiter, and especially compared to the rocky planet. It helps to understand that clearly Neptune lies above it, so there's less dense of this, and you do have quite a significant amount of object which is within this regime. The most interesting bits comes when you go down and you hit the green hatchet line here, which is the Earth. So 1,1 is exactly where it would be the Earth, and you take the Earth structure and you move it, assuming you can move, scaling up all the densities into the Earth, up to the point you reach a similar mass than Neptune's. The reason why I did that is I wanted to show you that you can explain a Neptune mass using the density of Jupiter using a density of water, something which is a mix between water and Jupiter, but also using a density of a rocky planet with almost no atmosphere like the Earth. And I think this is something to digest and to think about, because you do have objects all around here. And the big surprise is if you pick the mass of around 8 to 10 Earth mass, you will have to acknowledge we are experiencing an amazing amount of diversity at that stage. Well, then you can zoom in, and there may be talks about that. And there is a valley here, Fulton Valley, and there is a prediction. There is maybe the different structure. We're talking about different population of planet within a given mass. But the reason why I wanted to show you this is the end product when you form planet from a disk. So we will have to come up with something pretty clever here, because we will have to assume that the formation mechanism of planet can come from many different ways, because how would you get at the same time for a given mass planet which is so different? So this is the big challenges for the years to come. This is why people are conducting systematic programs right now. There is TESS and KEOPS space program. There will be Plato later on. And I think there is a huge interest to understand with way more detail what all these planets that are lying within a boundary where essentially you have no counterpart in the solar system. Bear in mind that between Neptune and the Earth, there is no counterpart in the solar system. So we are in a regime which is fascinating, because this is where we are found most of the planet orbiting the other stars in the universe. So quite exciting field to be in, where essentially the solar system is giving you only a hint what is the reality. Well, I don't want to dwell on too much on that, because I'm sure there will be talks about atmosphere of planet, and it's not my main field of competencies. But as a kickstarting the meeting, I just wanted to convince you that a lot can be made even when you don't see and don't have a direct imaging of a planet. Well, this is a famous light curve of a planet that is now becomes a kind of landmark. I'm using this as a textbook. It's a textbook light curve done by Kepler. When you have the transit, the time when the planet goes in front of the star, but also when the planet goes behind, that we call eclipse in the exoplanet jargon, and sometimes secondary eclipse. So this eclipse is a fascinating time, because this is where the planet is just behind the star. So this is the only moment when you look at the systems without resolving the system, when you're sure you only see the stars. Well, what is the relevance of this is anything else when the planet is out of this region will be the planet plus the stars. So you can play these tricks when you identify this eclipse here. This is a zoom on the bottom, and this is the star flux, stellar flux. Like in that case, can account quite significant bit of the flux, but all the rest is the planet. So the shape of this light curve, as well as the detail, if you do the spectroscopy, tells you a lot about the planet. It's not only about the atmosphere, it's also about the nature of the surface of the planet. If you have no atmosphere, you can learn something from the nature of the surface. People are studying object of the solar system just by looking at the spectra and the color, and they can get some good idea what is the material forming this object. We will do the same. We are going to do planetology of this planet. When there is no atmosphere, we just see the ground bottom of the planet, and that's the way it's going to work. Well, of course, the transit give you a direct also measurements of the imprint of the absorption feature you get into the atmosphere of the planet. In some case, you can combine both. When you have a thick atmosphere, you get some bit from the reflections, that is, some is reflecting from the upper clouds and then can go through other wavelengths, and you can combine all of this and to give you some idea about the atmosphere. So atmosphere of planet is really the next big game here, and there's a lot to hope for that, because the expectation is there will be some combinations about the density and the structure of the planet and the composition of some of the ingredients you have on some of these planets. And the big hope comes from essentially the big boys here, the big planets, because they have an imprint of the formation mechanism. When you move to the smaller planets, they tend to have a bit more complex evolution, because you have a lot of sinking into the planet, and you may have also the delivery impact that the smaller the atmosphere is, the more this will be impacted by the story of this system. And of course, the most extreme case, and when you're dealing with a rocky and small planet, the atmosphere you will get will essentially tell you nothing about the formation mechanism, except that if you are observing the planet at the very early stage, because it will just tell you what's going on this atmosphere at the time you observe it, which is a composition of many different scenarios, and combining the geophysics and also with the imprint of deliveries into this planet. So I would like to just spend 5 minutes, because sometimes there's a lot of debate about this habitable zone, and I'm usually using my time right now to make sure that there is no ambiguity about that. So habitable zone is something very, very simple defined. It is when you get liquid water. That's it. There's nothing else, nothing more. Of course, there is an assumption behind this, is the planet has to be rocky. So some people shortcut this because they have no evidence that the planet is rocky, but they can still claim that the planet is in the habitable zone, even if it's not rocky, while it would at the end means that the conditions for liquid water are more difficult to prove. But in the case it's a rocky, it means you can have the mass and the size of the planet and convince your peer the density is rocky, and it's the habitable zone, then potentially you have liquid water there. Well, you need two assumptions. The other one, you need to know the atmosphere of this planet. That's true, but if you're flexible enough, you can imagine plenty of different atmosphere, and that's perfectly acceptable, assuming you know the assumption you're putting in. So if you put hydrogen, if you put a lot of CO2, you can end up with different kind of scenario here, different kind of situation, but still you can still work out and define some kind of habitable zone regime. I think this is interesting because people get a bit obsessed by this, because behind that there is the fact that you can find life. The practicality of water is undefined entirely, because the fact is habitable zone doesn't mean that you have water, and the origin of the water on Earth is still subject to debate. The water can come from the inside of the Earth, but it also can come from the outside by deliveries. And this is something that nobody has a clear idea how you bring the water in at the right amount of time to produce life here. Now, leaving this aside, I just wanted to make sure about this. The reason why I mentioned that is most of the planets we have found, they are not in the habitable zone. Most of them are in short period. And that's the one for which we have the density. The one I've showed you before, essentially all the planets we've seen, they have a mass and a size, and they have a density which is rocky. So they would qualify, but they are not, because they're just too close. And we will have to live with that for a long time because of the principle of the transit, which is very poor at getting a transit for farther out object. Now, what do you do? Well, you change a star. And people are looking now, moving this assumption that there is a lot of planet orbiting at short period by the fact you could maybe extrapolate this will still be the case for M stars, low mass stars, and it is marginally the case, and still needs to be formally demonstrated, but there's significant detections on planets of that kind. In that case, when you move down the mass of the stars, the habitable zone gets closer, and this is why people get crazy about this habitable zone, because it turns out that some of the planet that has been found, they have a density which fit along the green line I mentioned to you, and they are within the habitable zone. So we are in this regime, exciting, where we do have planets that seems to be within a regime where you could get water in. It doesn't tell you very much about the history of the system, but it opens the prospect of looking for life. So I would like to use my 5 last minutes here to talk about life. There is a famous system, TRAPPIST-1. I don't know how many JWST proposals there has been on TRAPPIST-1, but I'm willing to make a bet it's more than a dozen on that systems. People believe that they should be able to find something that is maybe telling them about life on this system. So I just want to extrapolate a little bit on that and give you my 2 cents view of that. Well, first, I'm always very happy to show this beautiful diagram of Vicky Meadows about the diversity of the possibilities you can have about atmosphere of a planet, whether you have life or not. And the reason why I mentioned that is just to attract the attention of the astrophysicist for the geophysics. It seems crazy, but there is a lack of geophysical understanding of the nature of the rocky planets to really experience a full understanding what is the atmosphere of such a planet. We need to understand the geophysics of the systems if you want to understand the atmosphere of this planet. And Vicky Meadows put that very nicely by demonstrating here in a diagram that oxygen could be easily produced by breaking the water or breaking the CO2. You can play around all these games. This is just chemistry. And if you get the right amount of energy with the photons, you make it. So the fact you may detect oxygen and ozone in the atmosphere tells you nothing about life. I just want to state the obvious because there is still in the community a little bit of a misunderstanding what is about life. And all this is a valid question to look for life, but you can't look for life if you don't understand the planet. And you understand the planet only when you go to the geophysics. Well, I would push a little bit further, and I would like to stimulate interest for chemistry as well, if you want to do that. And maybe the geophysicists should start engaging with true chemists. When you look about life, essentially, you're looking at something very, very complicated, like something like that. Now, if you want to have a hint about the possibility of life, I think we should be better called to look at the building blocks of life. Really, what is the element that is making life possible? And what are the conditions, the astrophysical and the condition on the planet to make these building blocks just existing for life? And there has been quite a lot of work recently on that. And this is one of the famous building blocks. This is LEGO. This is the one that produces marvelous construction in the back. And I think we should do something like that. Well, in the case of the life, it's called the prebiotic chemistry. So if you don't know very much about this, and if you're willing to engage into the question of life in the universe, I really encourage you to open the textbook in the biochemistry to start learning about that, because you're talking about the amino acids here. You're talking about how you make the amino acid. Some of them has been detected in COMET. It's very easy to produce the simple amino acid because you use the energy of the UV light to break apart and to move around the electrons that is free on the carbon, oxygen, all these elements you have, water, carbon, all that on COMET to make some of them. The challenge here is how do you make the 20? Because life is made of these 20 amino acid. And it has been quite a recent advancement from the chemistry ground on that in the last 5 years, where the first complete model of chemistry built origin of life mechanism has been set. The progress is due to the progress in computers, because this is done in network computing chemistry. Essentially, you put into computers thousands of reactions at the same time, and you come up with a set of reactions that produce the ingredient for life. The good news for astronomers is you may have been told in the textbooks that life comes from the oceans. Well, maybe, but at least there is another maybe suggestion here that it is coming from the surface of the planet, which is pretty cool because that's something the astronomers can say something and do something about. Well, the first ingredient that, according to this chemistry, and I would just encourage you to have a look at these papers if you want more detail, is if you have water, which is seen as an essential, that's why the habitable zone is key here, and I think we should not discard the habitable zone, even it may be a bit complicated sometimes to understand what it is. You need also something interesting, which is SO3. SO3 is a direct production of the volcanic activity. So you need some kind of plate tectonics or some kind of volcanic activity going on. How come could you say something about that? How could you predict that there will be plate tectonic on the planet? That's a very interesting challenge for exoplanet, for the future discoveries of atmosphere. But there is some hope that we may be able to learn and say something about that. I just want to remind you that Venus has the exact mass and the exact size than Earth. So possibly 1 billion years old ago, Venus was like the Earth, a blue planet. Well, plate tectonic stopped and the CO2 recycling stopped, and then we ended up with a full greenhouse effect, and now it's kind of not the very most nicest place to live on. But this is why SO3 is critical here. HCN is seen as a very key ingredient. One way to deliver HCN for free, it's COMET. So studying COMET, cometary impact, understanding of the early stage of the formation are absolutely essential. And all this is coming at a very early stage of the formation of a planet. Well, atmosphere doesn't need to be special. Contrary to what was the origin of life in the 60s, people have been assuming a very energetic atmosphere. They don't need this, they don't need a reduced atmosphere, because the energy to do the chemistry comes from the UV. So the UV flux from the star is the assumptions being made in this paper to produce the 20 amino acids. The good news, with very simple ingredients, you can make the 20 amino acids. So of course you don't make life, the 20 amino acid is just the building blocks, but at least you understand one of the big mysteries is why all the proteins, why all the life is being built only on these 20 amino acids. And that's just a starting point here. So the reason why I mentioned that is I think there is an interesting dialogue to be made between the astrophysicists at different stage they're looking at, early stage in the formation process, and then the chemist and the biochemist into what is actually life and what is the ingredient which is needed for life. So I would like to end my talk with this recent work I've been doing. I did some experiment as an astrophysicist when I move an equipment into a chemistry lab. It is a wet lab doing biochemistry. And what I did is I calibrate the UV flux to understand how much flux the lamp was producing in terms of astrophysical content. So it was a very nice experience, a lot of laugh, because at the time we were reading the paper, we debate endlessly what is an error bar, because these people, they don't know usually how to deal with error bars, they don't really care. And what we demonstrated is this mechanism I was mentioning, this is essentially the work of Paul Rimmer, is the UV flux of the early sun is enough, that is demonstrated in this diagram, to produce the amino acid as it is predicted by this chemistry. So the interesting bit is we extrapolated the habitable zone to cooler stars, in this case the TRAPPIST. You see here this habitable zone, and the lower boundary to produce this, the right amount of UV flux, enough energy to produce the chemistry, is not met. So the conclusion of these studies is if life, the origin of life is indeed described by these equations, and if this is right for the Earth, the life could not have happened on TRAPPIST-1 on the same basis than the life we have on Earth. So you may have life, but it's not built on the same ingredients. At least you cannot produce the 20 amino acid the way it has been produced on Earth. So it's a note of cautions here that you can still deal with the M stars, you can still deal with finding habitable zone planet. At the end, you're not telling anything about life. If you want to deal into life, you have to get into the chemistry of life. And then you have to start adding a lot of other ingredients, which is the interface between the delivery mechanism, which goes back at some point to the disk, what you have in the disk, what is falling on the planet, and what is the interaction you have between the star and the planet at different stage of the history of the planet. Okay, I will stop here and wish you a very good conference and meeting. Thank you.
Thank you so much, Didier, for a fantastic talk. Just want to give some audio feedback since we're all
yeah, I know this is the strange part when you do this kind of Zoom meeting.
I'm sure everyone else is clapping also. And thank you so much for taking time out of your busy schedule to join us. We have a lot of questions in the chat, so I'll just try to capture a few of them. And for those, because we probably won't be able to get to all of them, the questions will be moving to the Slack channel. So everyone, please check there. And Didi, I hope you might have some time to answer some of the questions there. So let's get started. One of the questions is, how common is the solar system? And the specific question is, can you speculate about the reason why the solar system is so atypical in lacking a super Earth? Does it have to do with Jupiter or something else? And more generally, I think people want to know, is the solar system a weirdo, or is it, similar to other systems in some way?
Okay, there is two ways to see this question. So I thought a lot about that because I have the same questions. I don't have the clear answer, I mean, to be frank with you, but my way to see that is the following. Well, the only evidence of something similar to the solar system is the discovery of the giant planet like Jupiter. And we have few of them. Actually, we have about 5 to 10% of the Jupiter that seems to be orbiting in a circular manner. Though if you consider there is 5–10% of them, at the end is 1%. So 1% of the star may end up having a true Jupiter like our own. It means within this Jupiter, there may be small planets, but we just can't see them right now. So that's the kind of the fact you can put. Now, there's something else you can say as well, is we are looking at the universe. We are alive. And this is maybe why the system is what it is. So maybe all this other system, there is no life at all because the conditions are not met. So the reason why we are astronomers right now and having a Zoom conferences is because that system ended up like that and allow life to be developed. So it's more a philosophical statement because I don't have fact, except that I am alive, I'm talking to you. But this is my only way that I understand the situation right now. That's why I'm very keen at finding the other Earth. And I'm part of one experiment, it's called Terra Hunting experiment, when trying to push the only technique which I believe can make a discovery of that kind, which is the old-fashioned radial velocity techniques, which has the capability, the technology to do it. It's just a matter of getting enough telescope time. And you essentially have to steal a lot of telescope time to do that. It's like a long-term experiment, like a CERN experiment, when you have to dedicate a facility for 10 years to look for a handful of stars and to find out. I might hope we will get some numbers, but already the fact we have half of the planet that are different tell you that we are not common.
Okay, everyone. This could also be a potential poll for our conference. Well, there you have it. So let's see, another popular question. This has to do with, you challenged us to think about how do we get from disks to planets. So the question is, how much of the architecture of planetary systems is inherited from their formation? Or does secular evolution erase too much information to make those connections?
Well, I think this is a fascinating question. And frankly, if you look right now, there are two communities, and these two communities are not really meeting yet. And they are, on one hand, the disk community, which is dealing with a very early stage of the formation of the planet, and still are looking at the outskirt of the event. I mean, most of the action is going on within the last pixel in the middle. HLTau is very interesting because if you pay attention where is Jupiter, and you assume that the action is going within Jupiter distance, it's essentially the center. So all these wonderful disks we have are fascinating because they tell you something about the diversity and then kind of how common is a disk, but it doesn't tell you very much about really what's going on the planet. But it's a matter of time. I think there is nothing that prevents us to go into this detail, and there is equipment and future development. I'm looking forward to a kind of a new generation of interferometry techniques, maybe a slightly longer wavelength here to deal a bit more detail with what's going on. So I feel there's a lot to do, but still, we know quite a lot. I think we have right now this kind of, let's say, impossible, let's say this way, diversity of all these planets where it's supposed to come from nowhere. I mean, you have a planet that can look anything like as mentioned, Jupiter on a rocky planet with the same kind of mass. So essentially within the same distance. So practically the mechanism is producing a diversity like a city. I mean, people living in a city can come from different locations. At the end, they're all meeting in the city. So something is making the city. So gravity brings these people down. The disk interactions is pushing them down, and anything is moving the planet inside. That seems to be pretty the case. Well, maybe sooner or later, we're going to find out that there is a zillions of planets just floating around because they have been ejected. Because one of the consequences of the fact we have so much of this eccentric Jupiter is you have to acknowledge a massive planet-to-planet interactions. Well, if you end up with a planet eccentric, it means another one has gone, like you have in the binary stars. So the prediction is there is a significant amount of planet moving around, and it's just impossible to detect. So future missions, maybe a gravitational lensing mission may find out some of them, and there is a great hope here. We may be surprised that there is a big amount of planets just wandering around and into the universe. So you see, it's not as simple. I mean, the idea that you have the disk, you have the story, it is as if you would imagine, oh, you're born at that place, oh, I can predict exactly when you're going to die. And I think it's not going like that, because people are moving around and planets are moving around for plenty of different reasons why, and they are having a different history. And this history is captured by the structure of the systems. The structure of the system tells you something. In some cases, you have this story trapped into the atmosphere of the planet, and I think nothing has been done on that ground. So there is a whole universe here, and a James Webb Space Telescope, Ariel, and future mission of that kind will be extremely helpful to find out more. Not the smallest one, but I think the one Neptune's and Saturn like that are very, very interesting. And we may have also dramatic improvements into the modeling right now, because it's fair to say that the modeling looks pretty cool, but people are not modeling all the details right now. Why do you have this very detailed structure in the disk? I mean, could you explain me that? And it's not, I think everybody was surprised to see a kind of diversity, all this pattern into the disk. Oh my God, there are patterns on the disk. Of course they are patterns. Look at the sky, the clouds. You think they are all the same? They're all different, because a little bit of difference creates a lot of difference into the final product. So I think the diversity of the planetary formation has to be acknowledged. We're dealing with a global probability problems, but probability is predictable. So we just have to understand what are the ingredients here and how the ingredient mix up. At the end, my hope is when we'll have so much information on the planet, we'll have a clear pattern about why a planet is like that. It doesn't mean that when you have the disk, you will be able to predict what will be the outcome, but at least you will be able to connect why you end up like that and what was the path that drive this planet in that position and not in that one. And the fact we are the way we are, I think, is certainly another story, but it may be related to the origin of life as well. And that's maybe for later.
Great. Well, there were, as you can imagine, there were a number of questions about habitability, connecting up to your point.
Oh my God.
So let's see if I can, I'll just combine two questions. One question was, can you comment on the magnetic properties of planets and how that affects their habitability, particularly for M dwarfs? And what about the strong magnetic activity of these same M dwarfs? Is that a problem for habitability?
I love magnetic field because this is the magic mushroom everywhere. So if you want to make your life miserable, you add magnetic field. I think it's the case for the disk as well. So yes. I mean, magnetic field is essential. I mean, it's pretty clear. So, but there is many different ways to see it. I mean, there is a magnetic field of the planet itself, and definitely we would love to get something. Well, what we may be able to find out is not this one. It's the interaction between the magnetic field of the star and the one of the planet. This is what is being detected in IO in the radio. So there is big hope that something about the magnetic field may be detected at some point, but it's a very complicated problem here. Along SKA program, there is a hope that maybe the interaction between the magnetic field of some stars interacting with the magnetic field of a planet can be seen in some different conditions. M star, frankly, when you go down to the M star regime, when it's fully convective, nobody understands the origin of the magnetic field. I mean, it's not the magnetic field that the alpha dynamo process that you have on the sun. It's a different magnetic field, and it's a very explosive, eruptive magnetic field. This M star seems to retain a high level of activity, even very old. How come? I think the fact we decrease the angular momentum on G and K star is kind of well understood related to the wind interacting with the magnetic field. But for M stars, nobody knows really. And these M stars have been such a boring object for the past 50 years, but they are now becoming a very intensive, interesting object because of that reason. So I don't know about this, but clearly the magnetic field is a very serious element that should be considered. And any work along the way of the origin of magnetic field for M stars, interaction between magnetic field of the star and the planet, and what is the mechanism of the magnetic field? Is the discovery of magnetic field tell you something about the internal structure of the planet or the possibility of some plate tectonics or something like that? Would be a fascinating prospect. Or yes, please work on that. And again, this is at the boundary interface between the geophysics and the astrophysics. It's a great topic for study.
Another question that people have are about the asking you to predict the future. What what do you think will be the greatest, or I guess the advances or the future of the field of exoplanets in the next 2 decades? And that's related to other questions people had, like how close are we to really understanding the demographics of exoplanets in the solar system size scales and the demographics of planetary atmosphere compositions? So any field,
okay.
Yeah.
Okay, so let me tell you a story. I mean, you're going to laugh about this. So for so many years, we are playing a little bit of a game with people predicting the demographic of planet. At every meeting, we would have a chat with them and say, okay, could you please predict something? And next time we'll see whether you're right. And every time they come with a theory and they say, oh yeah, we're predicting this, predicting that. And the year after we came up with a planet they had not predicted, and that would just break apart the whole theory they had. Well, this is essentially what has happened in the last 25 years. So the theory has never been able to predict anything because it is very complicated. And they realized there is a lot of ingredient that we're missing. So essentially, some of my colleagues doing theory, they were arguing that maybe we should spend more money on theory and less on observation, because anyway, you guys are so much ahead of us. So that is really the reality of it. It's very complicated. Well, the outcome of this will be just because of the randomness of the process and the probabilistic nature of the process that makes this very complicated. So I would not take the risk of any predictions, but I certainly see that mission like the Gaia output, which is expected, and the catalog of astrometric discovery will just fill the gap. I see the progress being made by people conducting a high resolution imaging, and when they will be able to deal with the big telescopes, they definitely will bridge the gap between the radial velocity planet and the direct imaging, at least for the nearby object. And that would be a very fascinating prospect because we will get the emitted light. We don't have to rely then on the transit, which is very poor at giving you information of the planet. You will be able to track the flux from the planet all along. You will have season effect, you have a lot of different effects. So I think this would be really a major change when we will be able to get the flux from this planet whenever we like, essentially here. This is going to come. That's the purpose of this big telescope. The 39 meter of that was designed for the LT was designed on the rational element that we should be able to see a planet. That was the reason why it was not set up by a cosmologic requirement. That is the case of the other telescope. The ELT had a vision in a way because they implemented from the day one the idea that one day they may have the technology to make a picture of a planet, not only the extreme one that we have right now, but in a more general sense, any planet 5EU that is as old as our own solar system may be detectable. So I think that would be really a dramatic twist, because then we'll have an additional element here. But in the meantime, look, we have so many missions. We have James Webb. We have the TESS mission right now. We have Cheops. We'll have Plato soon. We'll have an Ariel. And the community keep growing. And then we're joining with the chemistry and all this geophysics. So anytime there is a new stuff. So I don't need to wait for 20 years. I think the fun is every week essentially coming. And there's new stuff coming every time, because there's so much data and it is so much of an exploratory domain where little is known, amazingly, after 25 years of discovery and 4,000 planets. It's amazing we know still so little about the solar system.
It's true. And one thing that I thought was really interesting in your combining a message from your talk and Laura's was the idea of serendipity, that there are so many exoplanet populations that we didn't anticipate. There's a lot more structure in the HLTau disk that I guess we didn't anticipate. And I guess that shows just the incredible richness of this field and why this is such a hot topic and a great conference. So Thank you, everyone. So thank you, everyone. I think it's time for, we're going to be taking a break now. And I want to thank all the speakers so far. And please have a look at the Slack channel for comments, questions, and potential answers. And let's meet back at half past the hour. Enrique or Alvaro, do you have any instructions or comments that you want to give at this point?
No, that's it. We're gonna set up a poll now during the break in case people want to start doing something after their bathroom break or something. But yeah, we're gonna reconvene at the 1/2 hour.
Okay, great, everyone. So let's meet back in 25 minutes. Thanks so much.
Okay, so let's start closing this poll. Pretty interesting results, 122 answers, so that's a good statistics. And let me, just for fun, let me show you now the same results that this question got back in 2016. There was a conference about HLTau. Sorry, I think, yeah, you go. Back in 2016, there was a conference right after the, well, about a year after the HLTau publication. And David Wilner asked this same poll. And this is the comparison of the results. So as you can see, planets has gone up, interestingly. MHD effects has gone up, chemistry has gone up, everything has gone up except other, and more than one has gone down. So I think that's a quite interesting result. Everyone can reach their own conclusions. Please feel free to discuss these things in the Slack channel, because I think this was a very interesting comparison. And I think John Carpenter will give the closing remarks to this conference. I think he will probably share his thoughts about this as well. Okay, so it's almost 1/2 the hour. So John, whenever you want, feel free to start introducing Meredith.
Joan, you're muted, I think.
Yeah, John, we don't hear you for some reason.
Can you hear me now? Okay.
Yes.
Awesome.
Yes.
Thank you. Thanks, Meredith. So in the last talk, Didier Queloz challenged us that those of us who love disks will eventually have to figure out how we get from the disks to the planets. And our next talk will cover one way that we can connect the disks and planets, and that's a topic of debris disks. That'll be reviewed by our next speaker, Meredith Hughes. Go ahead, Meredith.
Great, thank you, Joan. I'm going to share my screen. So thanks so much to the organizers for giving me the opportunity to give this review. So the conference is called 5 years after HLTau, but I thought I would title my talk 100 mega years after HLTau, because after all, that's basically what we're looking at when we are talking about debris disks. We're talking about what happens after the protoplanetary disk stage, not necessarily 100 mega years, as I'll talk about. There's a range of potential ages, but basically when we're looking at debris disks in the ALMA era, we're looking at a later stage of evolution. So, so what happens when we take HLTau on the left here and run this kitty clock forward? What do we see on the right here with ALMA? All right, so again, just to kind of get us oriented in terms of circumstellar disk evolution, the main distinctions between the protoplanetary and the debris disk stage is that protoplanetary disks are around pre-main sequence stars. They're very, very gas rich, 99% of their mass is in gas, and their dust is more or less agglomerative, right? It's undergoing this growth process. On the debris disk end of things, we're talking mostly about main sequence stars, generally less gas, much lower gas masses. I'll get into that a lot later on in the talk. And the dust is second generation. It's replenished from collisions of planetesimal-like things that have already formed in the debris disks. And so if you care about planets, you really care about this transition from the protoplanetary to the debris disk stage, because the conditions are really changing. And also the debris disk stage contains the imprints of the planets that have already formed in the disk. And just to remind everybody, you are sitting inside a debris disk right now. Our solar system hosts not one but two debris belts, one of which is visible with the naked eye in this beautiful picture from the observatory in Teide. Okay. So here's a little bit of vocabulary for you as we start off with debris disk. So when I'm talking about debris disk, I'll be talking about different parts of a debris disk. So I wanted to kind of go through that with you. And when we're talking about exozodies, these are the small grains that you see kind of highlighted in purple over here and down here that are mostly filtering in from some kind of asteroid belt analog. So the asteroid belt analog in blue and the Kuiper belt analog in green are the large grains. That's where the planetesimals are sitting, and that's where we see the ALMA emission coming from. And the only difference between those is the temperature. Asteroid belt analogs tend to be warmer than Kuiper belt analogs. And then Kuiper belt analogs in the outer part of the system, when those grinding collisions happen and you get small grains, they often get blown out in a halo, and I'll show you an example of that in a minute. And so when you look at the spectral energy distribution, you get some kind of combination of all of these different components, but it tends to be dominated by the Kuiper belt, the cold belts, and that's mostly what we're seeing with ALMA. So I wanted to also point out that two of the talks that you can see are about specifically exozodies and how they are related to outer belts, outer debris belts. So what is the relationship between the hot dust that we're seeing in the inner solar system and the cold dust that ALMA is probing in the outer solar system? So that's Jessica Wrigley's talk and Tim Pierce's talk, which you can see on the YouTube channel. Here, I don't have a poll set up for this. They only let me do one poll, which I'm going to do later on in the talk. But this is kind of a little quiz, but it's not really a quiz, since for not everybody here do I expect you to know the answer. But you probably have some intuition about what is and is not a debris disk, and so I wanted to kind of probe that a little bit, and just to think about some of these things that may or may not distinguish a protoplanetary disk from a debris disk. So go ahead and ask yourself this question: to what extent are debris disks gas-free as far as we can detect? So it used to be that, you know, I don't know, like 10, 15 years ago, when we would give talks, we'd say, well, protoplanetary disks have gas and debris disks don't. And then there was kind of an asterisk, well, maybe a few debris disks do, but most of them don't. And actually, ALMA has completely changed that now. So the correct answer is sometimes debris disks are gas-free as far as we can detect. But as I'll talk about later on in the presentation, the evidence now is saying that actually gas is the rule rather than the exception in terms of what we can see in volume limited samples of debris disks. So actually we think most debris disks have gas at some level, and in many systems it's detectable. To what extent are debris disks older than protoplanetary disks? So this is kind of an interesting question too. And this is another thing that we just kind of do without even thinking about it. I think a lot of times we'll introduce debris disks and say, yeah, debris disks are the ones that are around older stars. And I also want to point out that that's not necessarily true. And in fact, there's a talk in this conference that looks at potentially the youngest debris disk, one of the youngest debris disks certainly that's ever been observed. And so debris disks are not just a thing that happens around main sequence stars, but we can actually see them lurking in your sample of young stars in Taurus and Ophiuchus and Lupus and all of these young star forming regions that we think about. Some of those systems have already evolved to form debris disks, which is really interesting. So debris disks are not necessarily older than protoplanetary disks. Now, to what extent are debris disks optically thin at all wavelengths? I'm going to say always, but there's a little asterisk there, which is not if you look at the spectral lines necessarily. Some of the spectral lines are probably optically thick, actually, again, because of this gas that's so prominent in many of these debris disk systems. But in terms of the continuum emission, in terms of the distribution, one of the distinguishing characteristics of debris disks is that they are optically thin across all wavelengths. So the total amount of dust is much, much lower than in protoplanetary disks. You can basically see through it no matter what wavelength you're looking at. And then to what extent are debris disks undergoing destructive collisions? And we think that the answer to this has to be always, because if you look at the lifetime of a dust grain in orbit around one of these young stars, it's generally many times shorter than the age of the star itself. And therefore, we think that these dust grains must be constantly replenished through grinding collisions of planetesimals. So we think that the distinguishing features of a debris disk in this sense are that they are optically thin at all wavelengths and that they're undergoing destructive collisions, but we can't reliably use the presence or absence of gas or the age of a system as a distinguishing feature of a debris disk. Okay, so why ALMA? What role does ALMA have to play when we're looking at debris disks? So the answer is that debris disks look very different at different wavelengths. And so to show you an example of what that looks like, I have here the Fomalhaut system. And so these are 3 images of the same disk. This is the Fomalhaut debris disk. And on the left, you see a visible light image. In the middle, you see a far infrared image, and on the right, you see an ALMA image at millimeter wavelengths. So you can see that it looks very different, right? Even though, I mean, it has kind of the same general shape, this elliptical ring around the star, but at visible wavelengths, you really see the effects of scattering, and in particular, the likely forward scattering along this side of the disk. When you go to far infrared wavelengths, you get something interesting called pericenter glow. And that comes from this 1/r² dependence that as the starlight drops off as 1/r². So in an eccentric debris disk like Fomalhaut, one part of the disk is a little bit closer to the star. And so with that 1/r² dependence, a little bit of distance makes a big difference in the brightness. And so you get this glow at pericenter as it's scattering the light toward you. But if you go out to millimeter wavelengths, you see something that's actually very different. You kind of have to squint a little bit more, but the upper right part of the debris disk is in fact brighter here. And this is apocenter glow. And so what's going on here is that there are dust grains on eccentric orbits around the star, and they, and you know, Kepler's laws say that they spend most of their time far away from the star. And so you get a pileup of surface density at the part that's farther away from the star, and that's what gives you the apocenter glow. So at millimeter wavelengths, not only are we probing these millimeter sized grains, right? I have on the left here that the grain size is roughly equal to the wavelength of observation. That's a rule of thumb that comes from balancing the drop off of grain emission efficiency with wavelength against the fact that most grains are actually small. So the small end dominates the size distribution. So if you balance those two things, you find that in general, whatever wavelength you're looking at tells you roughly the size of the grains. So we're looking at millimeter sized grains, but also we're looking at we're tracing the density at millimeter wavelengths simply because of the different types of emission mechanisms that happen. We're looking at thermal emission from these grains. And so the temperature only goes as 1/√R. So it's not as sensitive, the brightness is not as sensitive to temperature. It really is sensitive to the density. And that's what gives you that apocenter glow. So, so we're looking at millimeter sized grains. And the other important thing about that, in addition to the emission mechanisms and the slightly different physics of how we observe these systems at different wavelengths, is that the grains undergo different physical processes. So here's an example from the AU mix system where the ALMA emission is the contours and the colors are HST scattered light. And what you're seeing here is not a sensitivity effect. This is a very real effect that the large grains, the millimeter sized grains, are confined within, in this system, about 40 astronomical units. And the small grains that you're tracing at optical wavelengths are blown out by radiation pressure to much larger wavelengths. So it's actually a different kind of physics that we're probing by looking at longer wavelengths. So small grains are affected by radiation pressure, stellar winds, whereas large grains are going to more directly trace the gravitational potential of the system, and in particular, the location of the parent planetesimal belts that are producing the dust. And so we see that very clearly when we compare ALMA observations with other wavelengths. And then finally, ALMA is great for molecular gas. So there are some ways to trace molecular gas at shorter wavelengths, but it's much harder. And ALMA is extremely well suited for rotational transitions of small molecules in cold gas. And that's what we're seeing in a lot of these debris disk systems. So the way that I'm organizing the rest of the talk here is I've basically just kind of tried to do sort of highlights of what has ALMA taught us about debris disk systems. So I'm going to start off with radial structure, azimuthal radial structure, azimuthally symmetric radial structure mostly. Then I'm going to go into some non-axis symmetry. Then I'll talk about the vertical structure of the disk, which is something that we could not look at millimeter wavelengths before ALMA at all. And then I'll end with a section on molecular gas, which has just been a field that has exploded in the ALMA era, not literally, thankfully. Okay, so I'll start off talking about radial structure. So this is from our annual reviews article that we wrote a couple years ago. But basically, when you look at radial dust structure across different wavelengths, like I've already emphasized with the AUMIC image, you see that you actually get slightly different results even for the same star, depending on what wavelength you look at. And this is showing at the time when we made this figure, which was now about 2.5 years ago, it includes all of the sub-millimeter observations that we had at that time, but it's definitely not up to date. And so on the next slide, I'm going to show you what actually is up to date. And so the point here is that if you look, these are organized by stellar spectral type A stars, F stars, all the way to K and M stars over here. And it's not really obvious that there are a lot of trends about where are these Kuiper belt analogs around these nearby young stars. But if you are incredibly careful with all of the systematics, which Luca Matra is, then one of the things that ALMA has allowed Luca to pull out is a planetesimal belt radius and stellar luminosity relationship. So on the y-axis here, you can see the planetesimal belt radius, and on the x-axis, you can see the luminosity of the star. And there's a lot of scatter, but there seems to be something there, and that might be hinting to us why planetesimal belts show up in the locations that they do. But if you really want to see the full collection of ALMA's resolved planetesimal belts, resolved Kuiper belt analogs, debris disks that that ALMA and the submillimeter array, kind of working jointly, have done up to this point, you're going to have to wait a little bit longer, but it's coming soon. So this is the reasons survey, and Luca was kind enough to share with me a sort of teaser slide here. And this is not even all of the sources that are covered in the survey. So so Luca has done the Herculean task of putting together all 65 resolved planetesimal belts, 50 of which are archival, 15 of which are new from ALMA and the submillimeter array, and doing uniform modeling of all of the visibilities. So, so Luca, you can ask Luca about that if you want to know more. But basically, it turns out that debris disks mostly are found in wide planetesimal belts. The narrow rings, like you think of for Fomalhaut, are the exception rather than the rule. So most debris disks seem to come in fairly wide configurations. And so you can see that in Sepulveda et al. 2019, and the full sample will be out soon from Luca. So, but let's dig into the structure a little bit more. What's going on? So this is kind of overview of all of the disks that have been resolved with ALMA, which is a lot at this point. But what's going on when you look in detail? And that's a really interesting story too. So one of the things that is going on when you look in detail at these resolved planetesimal belts is that now that we have enough observations with sufficiently high angular resolution and sensitivity, we're finding substructure in debris disks too, which is super exciting, right? I mean, this is the big thing that ALMA did with HLTau, is look for substructure in protoplanetary disks and really clearly showed these rings for the first time. And now ALMA is also allowing us to see some of the same things for these Kuiper belt analogs. And so here are kind of 4.5 systems. The half is because one of them is sort of tentatively detected, where we now see evidence for gaps or multiple belts in these debris disk systems. So you can see here's HD 15115, HD 107146 is just this gorgeous, I mean, it's face on, so it's really in your face. And we just have awesome signal to noise for this system as well, showing an inner ring and then a gap and then an outer ring here. And we see the same thing in HD 92945. HD 206893 is a new one on the scene, and then AU-MIC is the one that has tentative evidence. You can even see these two little lumps here on either side of the star. Those make little 3 sigma residuals when you subtract off a single broad Kuiper belt. And then there are other examples that are now coming to us from scattered light as well, which I put a few references in the bottom right here. But the cool thing is that we are seeing this substructure in debris disks as well as in protoplanetary disks. And with debris disks, we don't have as many options for making the structure because the gas masses are so low. And in most of these systems, and in many of these, I mean, all of these systems have a limit on the gas mass. And in most of them, it's significantly lower than the dust mass. So the effects of gas are probably not going to explain the presence of gaps in the system, at least not as easily as for protoplanetary disks. So, so maybe there are planets, right? Maybe there are planets carving these gaps. But one thing that's been kind of interesting in the literature is even seeing the variety of ways that people come up with to explain how you can configure planets to create gaps in debris disks. So here's a summary figure that was put together by one of my students this summer of gap carving mechanisms. And basically, some of the ways that have been proposed break down into sort of 3 categories. One is the center one is actually probably the one that you're used to thinking of, where you have a gap and then you stick a planet inside. But when you do these N-body simulations, you can actually come up with a lot of different ways as well. So for example, you can have 2 inner planets that are orbiting in resonance, and they create kind of a resonance chain in the disk, and that can create gaps farther out in the disk. Or you can even have a planet that's actually lower mass, that's comparable mass to the mass of the planetesimal belt, that then basically has this like secular resonance that gets induced, and so you wind up having a gap that opens up in the outer disk because of, as the planet's orbit circularizes, the orbits of the planetesimals are also affected, and they kind of clear out this gap. So that's the one on the right. And my student Anna went and tried to apply this to all of the different gap-containing debris disk systems that have been found so far. And obviously, embedded planets always work. That's kind of a given. But an interexcentric planet works for several of them, for at least 2 of the 4 that are really solid detections. 2 inner planets don't work as well. The resonance chain doesn't work as well, mostly because the inner edge of the disk is the inner part of the disk is too broad. You really have to get the planets pretty close to the first gap in order to have the resonance chain work. Okay, another cool thing we can do, so this is another cool thing we can do with resolved debris disk structure, is using debris to measure planet masses. And so this is something that I think we're really excited about being at this stage, and it's a real area of synergy with some of the direct imaging planet surveys that are going on right now, like with GPI and SPHERE. So here are 2 famous directly imaged planetary systems, HD 95086b and HR 8799. And whenever you have directly imaged planetary systems, there's basically always a debris disk there at some level. So planets and debris really go hand in hand. And it's kind of the most fun, well, one of many, many fun configurations when you have a debris belt outside the orbit of the planets. And so here's 2 examples of that, HD 95086 and HR 8799. And I just showed you their planetary systems, but if we put those on the scale of the millimeter images of the disk, you can see that they fit neatly right inside those little holes in the millimeter image disks. And on the right here, this Wilner et al. 2018 paper by David Wilner and collaborators, my favorite figure from that paper is not actually this image. My favorite figure from that paper is this constraint on the mass. This is basically a dynamical constraint on the mass of the planet, because if you look at where the planet is relative to the star, and you assume that the outermost planet is carving the inner edge of the gap, and you just use some chaotic zone theory approximation of how large a chaotic zone of a planet can clear around itself, then you can actually turn the location of the inner edge of the debris disk into a constraint on the planet's mass. And so here it is, right? We have this dynamical constraint that's now getting down. It's not quite precise enough to be better than the estimates based on models of hot and cold start evolution of directly imaged planets, but it's getting there. And so as the sensitivity and resolution of debris disk images increases, we'll be able to do better and better. Okay, so let's move on to non-axis symmetry. So what are we able to do now with non-axis symmetry? There are a few different kinds of categories of non-axis symmetry, I think, that ALMA has helped us to study in these debris disk systems. The first is eccentricity. And so I already showed this gorgeous ALMA image of Fomalhaut at very high resolution that Meredith McGregor is the first author on. There are a few other eccentric narrow rings that have been studied. Virginie Ferremas has one in the middle here, HD 202628. And on the right here is HR 4796A, which you actually can't tell is eccentric if you only look at the ALMA data. But in fact, you can learn something about the composition of the dust grains by looking at the, in this case, lack of apocenter glow for HR 4796A, which came as a bit of a surprise. So it turns out, like I said, that that apocenter glow is a really interesting thing that you can see at millimeter wavelengths that actually constrains the dust properties, and especially if you look at how the apocenter glow changes as a function of wavelength. So that's been a really exciting development that has kind of where the observations and the theory have sort of gone forward hand in hand. And Grant Kennedy also has a paper pointing out that the rings at millimeter wavelengths are actually much narrower than you would expect. And that implies that we should see narrow rings in the narrow eccentric rings in the protoplanetary disk stage as well. And so that's something that will be interesting to look for as we start analyzing in great detail these high resolution observations of the protoplanetary disk structures. And I also want to point you here to 2 of the talks that also deal with disks that have some level of eccentricity. Katie Krotz's talk on HD 106906 and Mark Booth's poster on HD 38206 at this conference. Halos are another non-axis symmetric structure that we see gorgeous images of in optical light, and ALMA has a really interesting role to play here too. So here are 2 of these systems that have these swept back halo structures, HD 32297 and HD 61005. And it turns out that the millimeter grains in the halo are, that when you analyze these data, I mean, it's not really obvious from these pictures, but when you look at the residuals, it is, there are millimeter sized grains in the halo, and that's really a surprise. Most of the ideas about where these halos were coming from seemed previously pre-ALMA were from like ISM interactions, things like that, where you would expect that the small grains would get entrained in the ISM, but not so much the large grains. But in fact, when we go and image with ALMA, we see evidence that there are actually millimeter grains in the halo of these objects. And that makes it more likely that it's some sort of dynamical effect potentially related to planets. And there were actually 2 papers that came out quasi-simultaneously before these observations by Meredith McGregor saying, hey, you know, planets are actually a viable mechanism for producing these swept-back structures in debris disks. And those are given on the right here, Esposito et al. 2016 and Li and Chang 2016 as well. So, so halos with ALMA are a really cool thing. And then another really cool non-axis symmetry is the presence of clumps. So there are some systems that have really obvious clumps. Beta-PIC is kind of the poster child for this, where we've already seen this image, I think, multiple times in this conference already, but you can see that one side of the disk is brighter than another, and the top is the continuum, and then the bottom is the CO gas. And that clump is really, really prominent in the carbon monoxide gas. So, so there is some level of clumpy structure in these debris disks, and especially in some of the older gas-rich planet-bearing. I mean, Beta-PIC is so interesting from so many different angles, but because we know it has a planet in it and multiple planets as well. So then there's also a category of, this is kind of interesting, and this is a little bit more speculative, but I think it's actually becoming sort of statistically improbable that all of the lumps that we're seeing in rings are due to background galaxies. So here's this beautiful image of HD 202628 that I already showed you when we were talking about eccentricity. But now I want you to focus on these little lumps in here, S1, S2, S3, and S4. And we don't know what these are. They're just, they're kind of knots in the structure that showed up. And you can calculate how many background galaxies are like the plague of debris disk studies at millimeter wavelengths. No offense to people who like galaxies, but we don't really like galaxies that much. So, you know, we spend a lot of time worrying about, like, is this lump a galaxy or not? But I think we're getting to the point where, I mean, you know, something with a placement like S1 where it's right in the ring of the disk. And if you read Virginie's paper, you'll see that she goes into the statistics of this, like, okay, you know, maybe you could expect 4 lumps in this image just by chance with submillimeter galaxies. But really, if you also think about what's the chance that one falls right on the ring, given the small area that the ring covers, it starts to look more improbable. And then we see other examples of this too, like in Mark Booth's study of Epsilon Arri, where there seems to be just this excess of brightness that also is located right in the ring. And, you know, there's nothing definitive yet, but I'm kind of interested in the likelihood now that we've seen so many of these rings, we're starting to see multiple rings where there are lumps like right in the ring. Is that a background galaxy, or could it be something else? So I think that's an intriguing indication that we'll learn more about as we get higher sensitivity images of many of these rings. And also in this category, you should look at Joshua Lovell's poster on Q1 Arri, which also has another very similar example of some sort of clump-like structure embedded in the disk. Okay, so now we're going to move on to talk about vertical structure, which is something that I'm pretty interested in. So, I'll spend a little bit of time talking about vertical structure, but I'm not going to start by talking about anything that that my group is working on. I'm going to start with my favorite vertical structure study, and this is Beta Pictoris. So again, we've seen Beta Pictoris a lot already, but that's because it's such an amazing system with so much to teach us about planet formation. So it turns out that if you look at this image of Beta-PIC is very conveniently viewed almost exactly edge on to our line of sight. So if you think about the possible range of inclinations, Beta-PIC is almost exactly 90 degrees edge on. And there's the star in the middle here. And if you just kind of look at this image, you see this spine of dark blue color here. And then you see sort of a fluffy top and bottom of the disk that's in that kind of lighter blue or turquoise color. And it's actually not your imagination, and it's not just a trick of the color scale, that you see that kind of narrow midplane and then that fluffier upper layer. So, Luca Matra has studied this in some detail. And so what you're seeing here is this is the flux in terms of the fraction of the peak flux as a function of vertical distance from the midplane kind of averaged along the disk midplane. And the red line here is the best fit single Gaussian fit. So if you just take the vertical structure of the disk and you try to fit one Gaussian to it, it doesn't work very well. And you have these significant residuals that you can see in the red down below. But if you actually go and fit a double Gaussian to it, so one narrow Gaussian to get that dark blue core, and then one wider, fluffier Gaussian to get that kind of turquoise upper layer, that's what you get in the green. And you see that it reproduces those kind of wings that you can see in the vertical profile, and then the residuals basically go away. And so when you look at a test of significance, this is statistically significant. It's a much better fit. And so it turns out that beta-pic actually has two dynamical populations. It's well described by two Gaussians, a superposition of two Gaussians. And you might have heard of another planetary system that has exactly the same thing. It's the one that we live in. It's the Kuiper belt. So we have the cold classical Kuiper belt, and then the hot scattered part of the Kuiper belt. So if you could go out and make this observation with ALMA, which you couldn't if we were around another star because our Kuiper belt is too faint, but if you could do this from another star, and you happen to be seeing our solar system edge on, you would see the same kind of double Gaussian description of what is going on in the vertical structure of our Kuiper belt. So this is really cool. It's starting to get really interesting from a dynamical perspective that we can see some shaking up of the vertical structure of these disks, and in particular substructure within the vertical extent of the disk. So another thing that's happening is that as we're starting to get more of these high resolution observations of debris disks, we're starting to be able to resolve vertical structure for a wider variety of these systems, not in as great a detail as Beta Pictoris, but in pretty good detail for some of the other systems. So one of the neat things about that is that it's telling us something about dynamical excitation in the disk. And if you interpret that through the lens of theory, it can actually help you probe the total mass that's hiding inside the disk. And this is something that we would really like to do. You know, in protoplanetary and debris disks both, we see some amount of dust with ALMA, but what we ultimately don't know is how much mass is locked up in large bodies that are invisible that we can't see. And this is one way of probing that, is by looking at how puffed up the disk are. So the cartoon version of why this works is because if you kind of try to embed a Neptune somewhere in the debris disk, then every time a dust grain comes nearby, it gets kicked, and there's some sort of equipartition that happens between the eccentricity and inclination, and the disk gets puffy. Whereas if it's stirred by a few Plutos, it's pretty flat. And so there are a couple of different ways of thinking about why this is important. One is the work of Philippe Thébault, who has shown, I mean, people have been doing this for a long time at optical and infrared wavelengths, so why should you care so much about the vertical structure at ALMA wavelengths? Well, it turns out that if you look at optical and infrared wavelengths, again, because of those physical effects that I was talking about earlier in the talk, you actually get a natural scale height just from radiation pressure alone that can be significant in those disks. And so it makes it hard to measure the dynamics if you look at the vertical structure at optical and infrared wavelengths, because the entire height of the disk can be explained by the puffing that happens simply because of radiation pressure. So if you go out to really long wavelengths like ALMA wavelengths, where the particle sizes are larger, then that natural scale height is basically down to 0 because the millimeter sized grains don't respond much or at all to the starlight in the middle. And so you're actually getting more of a dynamical picture of what's going on in the disk. And so if you interpret it through the lens of theory, Margaret Pan and Hilke Schlichting have this great paper where they look at the grain size dependent velocity dispersion in the collisional cascade. And so you can take a measurement of a particular grain size and kind of translate it into what is the total mass hiding within the disk. And it's incredibly sensitive. And if you look at their model, then recent ALMA cycles are able to get you down to, for a disk like AUMIC, which I'll show you in a minute, are able to get you down to a few Earth masses, which is pretty amazing. So it's incredibly sensitive to the total mass that's hiding in the disk. So one example of this is AUMIC, which is a paper that my student Cale Daly wrote in 2019. And so here you can see the observations. These are ALMA observations of AUMIC, and this is our model, and these are the residuals with those two tiny little 3 sigma blips that may indicate an inner belt, one on each side of the star that you can see here as well, that aren't well reproduced by the model. But basically, we were able to take these vertical structure measurements of AUMIC and put an upper limit on the total mass within the disk of about 1.6 Earth masses. And the asterisk there is that we don't rule out things that are outside the disk. So of course, we know that there are planets in the interior of the disk inside AUMIC, and there could be planets outside the location of the debris disk. But this is basically between semi-major axes of 20 AU and 40 AU. We're ruling out Neptune analogs in that radius regime. And there are a number of other systems now that have have similar constraints on their vertical structure. So there's some of that in the reasons survey, and then also on Josh Lovell's poster, he talks a little bit about the vertical structure of the disk that he's looking at in his poster too. And then you can also do a lot more fun stuff with vertical structure in these disks. And again, I'm just going to show this one example, partly because it's beautiful data. But basically, if you have two wavelengths, you have two particle sizes, right? Because like I said earlier in the talk, the wavelength of observation is roughly equal to the particle size. And ALMA can observe across a really wide range of wavelengths. So if you have two different widely separated frequencies, you're looking at two slightly different grain size populations. So we went out and imaged AUMIC at a factor of 3 difference in wavelength. And so here's the image that I already showed you. Here's the image at 450 microns. And so now you can go and you can analyze the vertical structure at those two frequencies, and you can measure both the size distribution slope and then also the velocity power law slope. So how puffy are they? What is the vertical structure at these two widely separated wavelengths or widely separated grain sizes? And it gives you some sense of where you are in terms of the strength regime versus the gravity regime, and what the velocities of your particles are like. And AUMIC, which is just one system, winds up way down here in the corner, which is basically telling you that you're getting erosive collisions between particles of similar sizes, which is not in line with the typical assumptions about how the collisional cascade works physics-wise. Okay, so that was all that I was going to say about vertical structure. And I'm going to spend the last kind of, what do I have? I have about 10 minutes before questions start. So I'll spend about the last 10 minutes of the talk talking about molecular gas. And I think that molecular gas and debris disks is one of my favorite stories of the ALMA era, because ALMA has really changed. I mean, it just feels like every day we're learning something new about molecular gas and debris disks. And it's not totally true, but it's almost true that every day we're learning something new about molecular gas and debris disks. So I'm going to try to sort of tell you this story, how it's evolved since the advent of ALMA. And I guess I should say that before ALMA, we knew that there was molecular gas in debris disks. I think the oldest indication of molecular gas in a debris disk goes back to around the 1990s or so. Well, actually, if you really want to go back to like Sledebeck 1978 or something, they saw some weird lines in Beta Pictoris. But you know, the most recent gas emission, or the earliest gas emission observation, comes from 1995, Ben Zuckerman's survey of molecular gas and debris disks. So we knew kind of all along that there were these peculiar oddball debris disks that had some gas, but ALMA has really changed our view of the demographics and the composition and the structure, and that's what I'm going to kind of talk you through now. So the first thing I want to talk about is that there are many ways to observe gas in debris disks, and just to give you an idea of the tracers. So you can look at atomic gas, you can look at molecular gas, those are the two columns here, you can look at emission, and you can look at absorption. And all of those things have been looked at before for debris disks. And in fact, there's a poster, or a talk, sorry, the talk, Isabella Rebolledo's talk, is on the connection between optical and millimeter emission versus absorption. And it's pretty cool. She has samples that go both ways, where she looks at, okay, where has ALMA detected molecular gas, and now what do we see with HST in terms of the absorption spectroscopy? And then she also goes the other way and says, okay, of the ones that have absorption features with HST, which ones do and do not have gas with ALMA? So you can go and look at her talk to learn more about that. So I'm going to focus on the top row here, the emission component, and talk about the atomic and molecular emission that's been observed with ALMA and how it's fit into this larger puzzle of what the heck is gas doing in debris disks at these late stages. So before we do that, though, I'm going to pause and have you all go to Slido, because before I tell you my side of the story here, I gave this poll to a bunch of debris disk people at a workshop last year, but I'm kind of curious, for those of you who have some opinion about this, what do you think is the origin of molecular gas? So historically, it's basically broken down into two possibilities. Over here, we have what several people have called Peter Pan disks, right? Disks that are, maybe these are protoplanetary disks that are refusing to grow up and evolve their gas away. Most of what we know about disk evolution comes from the dust, and so maybe the gas just sticks around from the protoplanetary disk stage rather than dissipating along with the protoplanetary dust like we've always assumed it does. Or the other possibility is that it could be second generation gas. So just like we know that the dust comes from grinding collisions of planetesimals, maybe there's gas that's released in these second generation destruction of bodies in the debris disk, and maybe that's where the gas comes from. So, so what do you guys think? Is it exclusively primordial, which would mean inherited from the protoplanetary disk phase? Is it exclusively second generation, which would mean liberated from grains or planetesimals or planets in the debris disk phase? Or is it probably a little bit of both? Maybe some systems are primordial and some are second generation, or are you just not sure and you kind of want to see what the rest of the room thinks? So go ahead and fill out the poll, and then I'll move on and kind of tell you the story as I see it. I will say that I still don't think that the answer to this question is completely settled or obvious. So that's kind of why I'm interested in the poll. Okay. So one thing that ALMA has told us unequivocally is that molecular gas is ubiquitous in debris belts. And so that's been shown in a few different ways. I have a whole laundry list of studies along the bottom here because there are a lot of people who have worked on this topic. I'm highlighting a couple of images here, but really it's been a process that's kind of taken the last, I don't know, 5 to 10 years to sort of sort out. But we've known for a while that the incidence is higher for A and B stars than for FGK stars. That in and of itself was a surprise, because if you think about where photodissociating radiation of carbon monoxide comes from, it's actually much higher in AB stars than in FGK stars. So that was a puzzle that has taken a while to solve, and I think now we have multiple potential explanations for why that happens. And now there's even a detection in an M star, which is really cool. So that's another one of Luca's papers that I'm showing on the right here. The TWA7 system has a detection of gas, which is really cool. So we're seeing stars of all spectral types that have these gas detections. And for A and B stars, for a long time, I was kind of joking that it's like, oh, go observe A and B stars with ALMA, get a free gas detection. It's great. It was like wherever we looked in A and B stars, there were these gas disks. And we also know that older stars are both fainter and less axisymmetric. And I didn't happen to put up the plot showing that, but you know, like we can see some gas in Fomalhaut, and it seems to be potentially concentrated around pericenter, which is pretty cool. So where does it come from? And I think here Canton Krall deserves the lion's share of the credit for figuring all of this out and showing us that there is a viable second generation production mechanism. So there's been a whole series of papers with him as first author, but here's one of my favorite figures from these papers where he's looking at the predicted CO mass in Earth masses as a function of distance, and then he kind of plots all of these stars and compares it to the sensitivity limits for some different instruments, APEX and ALMA, at different wavelengths. And so you can see that even at this time, this is 2017, we had detected a lot of the ones where the second generation model would predict that we should see it, we were actually seeing it. And so that's pretty exciting. But there were some cases, so there are a bunch of arrows here pointing to different systems, 49 SETI, 21997. There were some cases where the amount that we saw vastly exceeded the amount that was predicted by the model. And so the question was, okay, well, what's going on there? Are those not well explained by the second generation production mechanism, or are they maybe really protoplanetary? Oh, sorry. Did somebody say something? Okay. Are they maybe protoplanetary disks that have just held on to their gas? So we thought for a while, okay, well, there are a few that don't seem to be well explained by this mechanism, but most of them do seem to be well explained by this mechanism. So maybe second generation production is the main way that this happens. But then we got another update to this theory in the 2019 paper over here, where there's this there's this concept of neutral carbon shielding of carbon monoxide. So when you start to photodissociate the carbon monoxide, you get a carbon and an oxygen. And it turns out that neutral carbon, just by chance, happens to have an absorption band that's right where the photodissociation of carbon monoxide happens. So you can actually shield carbon monoxide with its own photodissociation product, which is really cool and extends the lifetime of these gas disks that we can see by orders of magnitude. And so that's really neat. So that seemed to say, okay, maybe even these very apparently massive disks could just be, it could be due to the neutral carbon shielding of carbon monoxide. But I also want to point out here this recent paper by Nakatani et al. 2020, where they're saying actually they think there's a primordial explanation for the presence of this gas. And it has to do with, and then it also naturally explains why it's more prevalent around A and B stars. And it has to do with the prevalence of small dust grains and the interaction between the small dust grains and the gas. So I'll put that here. There does seem to be now a viable theory that involves a primordial origin for many or all of these gas disks as well. But the neutral carbon shielding is almost certainly important, a really critical piece of this puzzle. And so there's additional support for this. When you look at what is the composition of this stuff, there's lots of neutral carbon. Here is one example. Aya Higuchi has done some beautiful observations of the 49 Ceti system. Gianni Cataldi has done this in Beta Pic and a couple of other systems as well. So now we know that there's lots of neutral carbon in some of these gas-rich systems. And we also know that there are very, very, very small amounts of other molecules, undetectable amounts of other molecules. And on the right here, I'm just showing a paper that's been submitted by my former master's student, Jessica Klusmeyer, doing a really, really deep survey, 5 hours of ALMA time in 2 different spectral configurations for a bunch of molecules, some of which are prevalent in protoplanetary disks, some of which are prevalent in comets, and we get really beautiful upper limits on all of them. And that's weird because actually, if you look at the line ratios for these gas-rich debris disks look neither like a protoplanetary disk nor like a comet. We're able to rule out both of those line ratios. And I think the key answer here is that it's the neutral carbon shielding. So whatever mechanism is allowing the gas to persist or creating it at these later stages, whatever other molecules are there are getting rapidly photodissociated, and only the carbon monoxide is able to persist because of the shielding by neutral carbon, which we see in great abundance, thanks to Aya Higuchi and Gianni Cataldi and others. So, but we can learn something about the composition of these gas-rich debris disks, and that's what I'm showing here. This is Luca Matra's work again in 2017. He looked at some of these gas-rich debris disks, Beta Pic, HD 181327, FOMO hot, and then compared them in terms of their CO and CO2 ice fraction relative to their total mass to solar system comets. So we have Halley and Hale-Bopp and Hartley 2 and 67P in red over here. And you can see that they're basically consistent. So this is really cool. This is giving us some of the first insight into the composition of exocomets potentially in these debris disk systems. And here's an update from Kral et al. 2020 showing a bunch of different systems for which we now have constraints on the CO and CO2 ice mass fraction. Again, the gray region here is basically solar system comets, and showing that it's basically consistent with solar system comets, which is really exciting. And then finally, I just want to point you to this awesome talk by Kanton Kral for the conference today, where he's showing that this has profound effects potentially on the composition of planet atmospheres. So we know that planets are present in the debris disk stage to some extent. And so if there are planets present in these gas-rich debris disks, which we now know is, like I said, the rule rather than the exception, that they are actually going to accrete significant amounts of potentially an entire atmosphere from the CO gas. And so he has this great Nature astronomy article looking at, basically this is the mass of the gas that it's accreting over the mass of the core and how that evolves with time for different accretion rates, and comparing that to the same ratio for present Earth, which is here at 10 to the minus 6. And you can see that over a time scale of about 10 to 100 megayears, many of these systems will exceed the current gas to core mass of Earth just from their accretion of material that's left in these gas-rich debris disks. So that's super exciting, and I think is really going to be an exciting connection to the field of exoplanets. All right, so just to summarize briefly, I talked about radial structure. Gaps in multiple belts are common. We can now place dynamical constraints on directly imaged companions by looking at their interactions with debris disks. Some planetesimal belts do have measured eccentricity, and there's the possibility of localized clumps in some systems that we don't understand the nature of yet. We're getting really excited about vertical structure. I at least am getting really excited about vertical structure, and I think everyone should be very excited about vertical structure. It's resolved for a bunch of debris disk systems now. It's a probe of collisional cascade physics, and at least in the case of Beta Pic, we're now seeing substructure in the vertical structure of the debris disk, just like the Kuiper belt in our own solar system. And then in terms of molecular gas, it's common, and we're getting insight into the structure and composition from ALMA, and it probably has really important implications for planet atmospheres. So thanks, and I'm happy to take any questions that you have.
Thanks, Meredith. I hope my sound is working.
Yep.
we've got some really terrific questions coming in from Slido. So, should we go over the poll first?
Yeah, I want to see the poll.
Yes. Okay, let's go over that first.
Okay. Interesting. All right, this is really cool.
Do the answers surprise you?
What's that?
Do the results surprise you?
I think, you know, I think that they're a little bit different than when I asked a year ago. I think a year ago, there were more people who thought it was exclusively or primarily primordial, i.e. inherited from the protoplanetary disk stage. And so that has changed a little bit in the last year. And I suspect, I didn't write down, it was basically a show of hands at the workshop last fall. But my impression was that there were more people last fall who thought it was exclusively second generation, and that maybe more people have now gone into the little of both category at this point, which is kind of interesting. That's just my impression. I don't know. I'd be interested to know if anybody has changed their mind since last fall in this survey. Yeah.
Okay, that's great. That would be a great topic for the Slack channel. So a very popular question on Slido comes from Heike Smulders, who asks, this is a question about connecting up the protoplanetary disk phase with the debris disk phase. Why do debris disks need a gap carving mechanism? Couldn't debris disks form with gaps in them directly from the rings that are seen in protoplanetary disks?
Yeah, that's a great question. So yeah, so to some extent, I think it's going to be a chicken and an egg problem. You know, what is the gap carving mechanism at the protoplanetary disk stage, and then what is the evolution like in between the protoplanetary and the debris disk stage? And I think both of those are still kind of up in the air. So the extent to which debris disks inherit their structure from the protoplanetary disk phase is, I would say, still a very open question. It's certainly possible, and you know, I mentioned that that Grant Kennedy paper where he's talking about how some of these narrow eccentric disks might have to be inherited from the protoplanetary disk stage because of the role of the gas in apsidally aligning the dust grains, basically. But I think for other models of debris disk structure and evolution, there isn't as much inheritance from the protoplanetary disk stage, and then what we're seeing in the debris disk stage is more about, you know, the underlying mass of planetesimals and how it evolves with time, and which parts of the disk are being stirred at different times and which are not being stirred at different times, and things like that. So I think there are it's a perfectly reasonable and excellent question to ask. So maybe we don't need to worry about gap carving mechanisms in the debris disk phase, but I would say that there is certainly no consensus at this point that debris disks primarily or exclusively inherit their structure from the protoplanetary disk phase. And there are a lot of biases at this point in terms of the radius regimes that we're probing. But if you try to do, I have tried to do this before, and if you try to just do like, okay, where are the rings and the gaps in protoplanetary versus debris disks, the distributions do look pretty different, at least right now. So like I said, there are a lot of biases involved with that, so I'm not sure it's a fair comparison at this point, but that's something that you'll see more of. I think Luca talks about that in the reasons paper as well. Okay,
cool. And I guess a related question is, in addition to the locations of the structures, the widths of the structures, and one question from Minky Vandermar was, I'm confused. The Reasons survey stated that the millimeter rings are wide, but Kennedy et al. 2020 says the rings are narrow.
Yes. Okay.
Is that a real difference, or?
I would love to disambiguate this because there's so much here to unpack. Okay. So, so Reason says that narrow disks are less common than wide disks, but narrow disks do exist. Fomalhaut is an example of a narrow disk. HE202628, Virginia Faramaz's disk is an example of a narrow disk. And so these eccentric rings, if you see an eccentric ring, it should be wider than it looks because of the degree to which grains should or should not be apsidally aligned. So narrow rings, narrow eccentric rings are very surprising. Okay, narrow eccentric rings are surprising, and we see multiple examples of them, which is also surprising. That said, if you go back to the recent survey and you look at, okay, what's the overall prevalence of narrow versus broad? Narrow is the exception, broad is the rule, right? But then when you look at broad disks at high resolution, and those are the images that I showed you that have gaps in them. So then so Reasons is all basically low resolution. It's what's available. So most debris disk observations are low resolution at this point because of our sensitivity limitations. So then if you go and you look in detail at the ones that Reasons would say are broad, what you find when you look in detail, and this is very analogous to kind of the HLTau experiment here. We used to think HLTau was broad, right? And then you looked at it in detail and it was a series of rings. And that's more like what we're seeing now with the debris disks, where if we take some of those broad disks and we resolve them, we're finding that there's substructure. So it's a lot more nuanced than that. So basically, Reasons is telling us that these single narrow rings are the exception rather than the rule. Most disks look broad, and then when we go at higher resolution and look at the broad disks, we're finding substructure. So thank you for allowing me the opportunity to disambiguate those statements.
Fascinating. Sounds like there's some really interesting stuff ahead there. Okay, now this is an important question a clarification question from Jake Simon. How exactly do millimeter grains in halos result from planets? Could you explain that part?
Okay, I can try. So this is me trying to explain my understanding of what the theorists are saying. My understanding of what the theorists are saying is that there's some kind of right-hand rule thing going on here where you have an eccentric planet and it's basically torquing the dust and then causing the dust grains dynamically now, because of the gravitational influence of the planet, to have one preferential direction where these halos are forming. Now, I do not trust my understanding of the papers beyond that level. So I'm going to have to refer those questions to, I don't know if Eugene Chang is here, or Eve Lee, or I'm trying to remember, it's Mike Fitzgerald, or who's the first author of the other one? I'm blanking right now, but yes, I'm going to have to refer more of those questions to them. But basically, my understanding is some kind of a right-hand rule involving torque, and it makes these halos.
Hey, great. Sounds like we should go to the papers. Okay, another question from Farzana Meru. You described using debris belts to infer the planet mass interior to the belt. What kinds of constraints are available on the rest of the planet masses in the system? I think you mentioned
yes,
the height of the disk. Yeah.
Yeah, well, okay, so there are two things here. So it sounds like that question was more about the chaotic zone constraints on the planet masses, and so that's the situation where you have the star, and then it's orbited by a directly imaged planet, and then you have a debris ring outside of that. And so so she's absolutely right whoever asked the question is absolutely right to notice that in many of those systems there were 4 planets, and I was only telling you about the constraint on the outermost planet, and that's because we can really only constrain the outermost planet. The planets interior to that, you can't constrain via this mechanism, because you really need to be measuring the extent of a single planet's chaotic zone, and you can only do that when there's dust in the neighborhood. If there's no dust in the neighborhood, which would be the case for the inner planets, then you can't do it. You can only look at the outermost planet that's directly interacting with the dust. Now, in the case of vertical structure, there's a lot of ambiguity there, which I didn't go into about, so you can get a total underlying mass measurement, but you can't tell what it is, right? Let's say that you get 5 Earth masses. You can't tell whether you have a single 5 Earth mass object that's kind of dynamically stirring your disk, or whether you have 5 1 Earth mass objects that are kind of all packed in there dynamically stirring your disk. So there's a lot of ambiguity involved in the interpretation of the vertical structure, but as a way of saying, what is the total mass reservoir underlying these disks? It's the best thing we have right now. It's still very useful. And when it's low, like it is in the case of AUMIC, it does allow you to rule out Uranus and Neptune analogs between radii of, in this case, 20 to 40 AU.
Okay, and it looks like that answer is related to another question someone had, which was in beta pic, the puffiness of there's a narrow and a puffy component. The puffiness appeared similar at different radii. If that's true, what does it say about the radial distribution of the embedded mass?
Right. Okay, that's a great question. And this also, so this is really another dynamicist question. It's probably also a question for Luca, who's the first author on that paper. But my understanding is that there's a lot to be said about time scale. And so you would really have to do a calculation of, at those radii, for a given planet mass located at a particular distance from the star, what is the time scale over which their influence would kind of propagate out through the disk? And so, so it's possible that a single planet could be responsible for the vertical structure throughout the radial extent, but it's also possible, again, I haven't done the calculation for the beta pic system, it's also possible that there could be a configuration where in order to sustain the same height across the radial extent of the disk, you would need multiple planets. But I think my impression in beta pic is that it's pretty consistent with stirring by some, and you know, there's also, there could be events. I mean, I think it's probably more related to like what we think happened in the Kuiper belt, where you have a planet like Neptune kind of migrating and then scattering a bunch of Kuiper belt objects. So it's probably related to something like that, where there's migration of a planet, scattering a bunch of objects, and then that's responsible for this scattered belt that we're seeing in our solar system and then in beta pic.
Right, okay. Another question is from Daniel Price. Many of the debris disks contain gaps and cavities observed with ALMA. Could large companions like binaries or planets make them look old when actually they're young?
That's an interesting question. So I'm not sure I'm understanding exactly where this question is coming from, but I'll try to answer it as best I can. In terms of the ages of these systems, so ages of isolated debris disks hosting main sequence stars can be very challenging to constrain. So, but for some of these debris disk systems, they're part of young stellar associations where we actually have a pretty good handle on the age through like a moving group analysis or some kind of, you know, like beta pic moving group. We have a better handle on the ages of those stars than we do for a truly isolated star that doesn't belong to one of these young moving groups. So, I think the ages are always going to be uncertain, but I don't think it's that. I mean, you know, I think they're probably. It depends why you're concerned about the age, I think, and so again, this is one of those situations where a back and forth would be helpful, which I can't have right now. But it depends why you're concerned about the age and to what precision you're concerned about the age, I guess.
Sounds like something we can take up in the Slack.
Yeah, absolutely.
Okay, maybe just two more questions. AUMIC shows very different radial structures in the visible versus the radio.
Absolutely, yeah.
But why is it that the Fomalhaut observations show similar radial structures in the different wavelengths?
Yeah, those are great questions. So, I think there's a lot to be learned about the comparison between the optical and the millimeter. And so for the case of AUMIC has all of these really interesting, so it has the halo, first of all, which I showed already, and then it has the fast moving features, which are really cool, right? There are these features that are moving out in the disk. And we in Daly et al. 2019, we did a really careful analysis of our radial structure compared to the radial structure that we see at optical wavelengths. And we don't see those features. There's no evidence of those features, those extra little density bumps that you see at optical wavelengths. And so that's telling you something about the grain size distribution. That's telling you that those fast moving features are composed entirely or primarily of really small grains. And so it's similar to like when I was talking about the halo, the fact that the large grains do seem to be populating the halo is telling you something about the mechanism that's sculpting it. I think the comparison between the optical and millimeter morphology is telling you something about the mechanism that is causing the fast moving features or some of these other things that you're seeing in the AUMIC system. And then I'm trying to remember there was maybe another part of the question there. But basically, I mean, I think that's basically the answer, is that when you're seeing similar structure at multiple wavelengths, it was about Fomalhaut, right? So when you're seeing similar structure at multiple wavelengths, that's telling you that it's some kind of achromatic mechanism that is sculpting the whatever structure you're seeing. Whereas if you're seeing differences between the optical and the millimeter, that's telling you that it's some kind of grain size dependent mechanism that's sculpting it. So I think there's a lot to be learned from the physics, and it's really, you're right to point out that it's very interesting when we see that some systems do exhibit similar structure across the electromagnetic spectrum, and some systems have very different structure across the electromagnetic spectrum.
Thanks. And just as in the final few seconds, I just wanted to offer the opportunity for you to look into your crystal ball and let us know what you are looking forward to or expect to see in your field in the coming decades, say. Will there be a revolution in studies of debris disks like the HLTau observation for protoplanetary disks? Have you already seen that, or what are your thoughts on the future?
Yeah, well, so I think I mean, the last few years, I mean, if you couldn't tell from the citations in here that we're all like in the last 5 years, the last 5 years have, I think, been revolutionary for debris disks. And I mean, I like to say, and I don't know, I mean, this probably sounds kind of less exciting than I think it is, but I mean, I think that we are now with ALMA, it's not an easy comparison to make because, of course, debris disks are on average closer than protoplanetary disks, and so you get kind of more bang for your buck in terms of linear resolution. But you know, in terms of like delta R over R, how resolved these disks are, we are basically with debris disks now where we were with protoplanetary disks in the pre-ALMA era of like submillimeter array and KARMA, where we're starting to see substructures, we're starting to see hints of these interesting things. And you could do a lot with protoplanetary disks pre-ALMA, and that's kind of where we are with debris disks now, which is exciting because pre-ALMA with debris disks, I mean, there were a couple of images, but it was like a blob here or there. And now we're seeing radial belts, and we're looking at all of this gas. I mean, ALMA has just been amazing for gas. We wouldn't have known anything about the gas and the composition of exocomets, right? Like that was unimaginable pre-ALMA that we could do some of this stuff. And now we're doing it for entire samples of objects. So we're starting to get some of that sort of statistical power of samples that protoplanetary disks had even pre-ALMA. And you know, I think in the future, there's a lot to be done with kind of more, I mean, my favorite thing is to go into the detailed structure of some of these bright debris disks and learn about all of the physics that we can by really maxing out the sensitivity and therefore the resolution with ALMA. So I think there's more to be done there for specific systems that have still really interesting things to tell us about the dynamics of disks and planets. And then kind of, you know, looking to the future, what happens next? I think ALMA bandwidth upgrades are going to be amazing for debris disks. I mean, we really are, debris disks have always been a sensitivity starved field. and, you know, pre-ALMA, we had the resolution to observe debris disks at kind of, you know, AU scales, but we didn't have the sensitivity to take advantage of it. And now we're getting that sensitivity, and kind of the more sensitivity that ALMA can give us, the more we'll really be able to probe down to those really interesting planet-like scales. So that's something that I'm excited about as well.
That's awesome. Well, thank you so much for a wonderful talk, and thanks to everyone in today's session for the fantastic presentations. Enrique, would you like to give any instructions before we end here?
Yes, so let me say that there's going to be a 15-minute break right now, and we're going to come back at the 45 minutes past the hour for about 30 to 40 minutes of short presentations given by poster presenters and also by contributed talk speakers. So don't miss that if you want to have a quick summary of some of the contributed talks that we've received so far.
All right.
And if you are a presenter of the short presentations, please stay connected so that we can promote you to panelists.
All right. Thank you, everyone.
Thank you, John. Thank you very much. Thank you for the speakers. Okay, so we're gonna start now. 1 second. Okay, so to all presenters, keep in mind that we're gonna have to do this very quickly. So the time limit is gonna be very strict. So whenever we reach 1.5 minutes, if you haven't finished, we're gonna have to mute your mic and go on to the next speaker. So please stay in time. So I'm gonna start sharing the screen with all the slides. And Jehan Bey, you go first. Go ahead. There you go, Jehan, you're unmuted.
Okay, yeah, I was not able to unmute. Okay, hello everyone, my name is Jehan Bey and I'm a postdoc at Carnegie Institution. In my talk, I introduced buoyancy resonances as a new mechanism through which planets launch spirals. So the idea is the following. So when you have a gas blob in a disk and it is perturbed vertically in this cartoon, right? It will oscillate at buoyancy frequency, which is determined by thermodynamic property of the disk, right? When that buoyancy frequency matches with the orbiting frequency of a planet, then those resonant interaction can amplify the buoyancy oscillation. That's what we call as buoyancy resonances. So in this paper we just submitted, we showed that for Jovian mass planets, buoyancy resonance can be quite strong, as large as 100 meters per second in terms of perturbed velocity. So we can observe this using with ALMA. And in particular, we proposed that a sub-Jovian mass planet in TW Hydra can explain gas motion in the disk. So if you look at the left panel on the top, this is probably what you typically see in planet disk interaction simulation, where things are assumed to be isothermal, where you don't see buoyancy resonances. Now, if you take into account more realistic thermodynamics and thermal properties, you can see all these additional spirals, which are through buoyancy resonances.
Thank you very much, Jehan. Next speaker is Katie Krotz.
All right, hi everyone. My name is Katie Krotz. I am a PhD student at the University of Victoria, and my talk is on the asymmetrical debris disk HD 106-906. So for those who are not familiar, HD 106-906 is a very interesting system that has an edge-on debris disk, which features several asymmetries. So one, the main disk belt features a brightness asymmetry where we see the left side is brighter than the right side. And then secondly, looking at larger radial separations with HST, the disk halo features this needle-like extension, which you can see in the left figure. And then finally, the system also has a large planet companion far outside of the disk. And this raises questions about the planet's role in the disk asymmetries. So this leads to my work with HD 106-906, where we have obtained new pole data with GPI in the JH and K1 bands. And our observational analysis of this data has led to some very exciting results, such as we find evidence that the disk belt is eccentric and is most likely caused by the planet companion. So that's a very brief summary. And if you would like to learn more, please check out my talk. Thank you so much.
All right, thank you, Katie. So next one is Laura Flack. Please, Laura, go ahead.
Hi, I'm Laura Flagg, a PhD candidate at Rice University. My collaborators and I work on finding and characterizing the youngest hot Jupiters. And one such planet is the 2 million-year-old HLTau b discovered with radial velocity observations. I work to confirm the planet's existence based on a detection of CO from its atmosphere using high-resolution K-band data from IGRINs, as you can see on the figure on the left. Each row is a cross-correlation function between the planet's spectrum and a CO template. And you can see its signal from the planet at the systemic RV of the star and the planet's velocity amplitude. By measuring the velocity amplitude of the planet, we broke the M sin I degeneracy and calculated at 11.6 Jupiter mass for the planet, making it the youngest planet with a dynamical mass measurement. We were also able to estimate the planet's magnitude based on the strength of the signal. We calculated an absolute K magnitude of about 8.2. Plotted on the right are young planetary mass companions as of function of age and magnitude. CI tau B is the one on the upper left with the arrow pointing to it. As you can see, it and all the other planet candidates have magnitudes consistent with hot start formations, meaning they lost little initial entropy during formation. However, only CI tau has an independent mass, along with beta PEC.
Thank you, Laura. We have to move on. Next speaker is Jean-François Gonzalez.
Hello, everyone. I am Jean-François Gonzalez from the Centre de Recherche Astrophysique de Lyon. The talk I'm advertising today is about spirals, shadows, and precession in the HD 10453 system. This is a binary star system in which the primary is surrounded by a large outer disk exhibiting spirals, much smaller inner disk casting shadows on the outer disk, and a gap separating both disks, likely caused by an unseen inner companion. My talk is the first of a two-part study and focuses on the outer system, namely the outer disk and the outer companion. We selected 7 orbital solutions from an astrometric fit of the small observed arc of the secondary star's orbit, shown on the left plot, in the plane of the sky in the top panel and the perpendicular plane in the bottom one. We used these orbits in hydrodynamical simulations of the gas and dust disk, all resulting in different disk morphologies, as can be seen on the right plot. The talk will show how we compare synthetic images from these simulations with observations to show that a circular and coplanar orbit is ruled out and that the orbit is eccentric and inclined with respect to the disk plane. The second part of this work about the inner system will be presented in a few minutes by Rebecca Nealon. Thank you.
Thank you very much, Jean-François. Next speaker is Rachel Harrison.
Hi, everyone. My name is Rachel Harrison. I'm a PhD student at the University of Illinois, and my talk is on determining upper limits on the magnetic field strengths in AS209 using Zeeman splitting observations. So Zeeman splitting from astronomical sources shows up as circular polarization in spectral lines. And with ALMA observations of multiple hyperfines within the CN 2:1 line, we were able to set upper limits of a few mellogauss on the toroidal and vertical magnetic field strengths in the disk. And we were also able to determine that if accretion in the disk is driven primarily by magnetic disk winds, then magnetic fields with strengths near our upper limits would be strong enough to drive accretion at the rate previously estimated for this source. So I hope you'll check out my talk, and I look forward to talking with you all during the conference. Thank you.
Thank you very much, Rachel. Next speaker is Jeff Jennings. Jeff, go ahead.
Yeah, thank you. My name is Jeff. I'm a PhD student at the Institute of Astronomy in Cambridge, UK, and I work on super resolution interferometric imaging techniques. So my talk gives an overview of new dust substructure trends identified in the D-Sharp survey by applying to all 20 sources the super resolution model Frankenstein, or just Frank, which is an open source code that fits a visibility distribution non-parametrically to reconstruct a disk's 1D brightness profile. So in the talk, I first motivate using a few of the D-Sharp data sets why applying such a model can be expected to constrain substructure at higher resolution than we obtain using the clean algorithm. And then I demonstrate the Frank fits more highly resolved disk gaps and rings, as well as identify some new features. On this slide, I'm showing an example with one of the D-Sharp data sets for SR4. So looking across the entire survey, in the talk, I then summarize new trends in D-Sharp, some of which include substructure in all of the survey's compact disks, inner cavities in 2 of the oldest D-Sharp sources, inner disk substructure in the spiral sources, and new features in the most structured disks. And finally, just in case you're interested in the code itself used for this analysis, I have a poster that gives a bit more information about it. And the poster Slack channel also has a link to a short video that demonstrates how to run this fit that I'm showing you for SR4 from the terminal in one line in under a minute. So thanks so much.
Thank you, Jeff. Next speaker is Caroline Kimmich. Caroline, go ahead. Caroline. Wait, are you there, Caroline?
Apologies. maybe move on to Giuseppe, and then we'll go back to Caroline.
Okay, sure, yeah. Let's go to the next one, which is Giuseppe Lodato. Giuseppe, can you, there you go.
Yes,
You're muted,
hello.
Giuseppe.
Yes, thanks. My name is Giuseppe Lodato. I'm from the University of Milano, and the title of my talk is The Theory of Kinks. In this talk, I will present a simple semi-analytical model for the velocity perturbations induced by a planet that is embedded in the disk. And I will show how, by using this model, we can reproduce, without the need for complex hydrodynamical simulation, the shape of the kinks that are often observed from our observations. Now, we believe that through this model, we can build up an efficient fitting procedures to get the planet properties based on observed kinks. And at the same time, on the contrary, we can use this model to predict what kind of kink amplitude we should expect based on some suspected planet that we know from other diagnostics. So come and see my talk, and I'll be happy to answer questions and comments. Thank you.
Thank you, Giuseppe.
You can go
yeah,
back.
Caroline is back, right?
Caroline now. Yes, it was my fault. Sorry.
Yeah. There you go.
So, did you ever wonder if magnetic disk winds might influence planetary migration? We know that viscosity can, but through other angular momentum transport mechanisms as well. I'm Lina Kimmich, working in Heidelberg in Kees Stulleman's research group. Magnetic disk winds are very complicated to model in full MHD simulations. That's why we decided to create a 2D model, not explicitly treating the magnetic fields, but the influence of the magnetic field on the radial flow of the disk gas. We find that under certain conditions, outward migration is possible. And you can understand that by looking at the sketch on the right. If the wind drives a strong enough inward gas velocity to partially fill the gap that is created by the planet, a mass excess in front of the planet occurs. And the planet is accelerated by this mass excess and migrates outwards. This result is very important because viscosity, on the other hand, can mainly explain inward migration. So to sum this up, we found that through wind-driven accretion, outward migration is back in the game.
Thank you very much, Caroline, and sorry for that. So next speaker is Jens Kammerer. Sorry if I mispronounced that.
Yes, hello everyone. My name is Jens Kammerer. I'm a PhD student at ESO and ANU. And I uploaded a talk about the recent results from the exogravity team. So what we do is we observe exoplanets in the K-band with the gravity interferometer. And in this talk, I'm presenting our recent detection of the gas giant Beta Pictoris C, which is the first direct detection of an exoplanet predicted from radial velocity observations. And by combining the RV data with the precise astrometry of gravity, we obtain a tight mass constraint for Beta Pictoris C, which suggests a formation via warm start core accretion for this planet. Moreover, we also obtained K-band spectra and precise astrometry of the PDS-70 protoplanets. And there we were able to obtain a dynamical mass constraint and also a constraint on the circumplanetary disk size of PDS-70b. Right now, we are looking at HD 26893b, which is the reddest known substellar companion. And thereby combining our gravity spectrum with data from SPHERE and GPy, we try to better understand the properties of the dust clouds in this object. So if all of this sounds exciting to you, please come and check out our talk about planet formation with near-infrared interferometry. Thank you very much.
Thank you very much, Jens. So next one is Michael Kuffmeyer.
Yeah, thank you. Wow, that was my reaction when seeing this beautiful image of dust rings and gaps in HLTau. And apparently many of you felt the same way as we saw in the poll. And a lot has happened since that press release, I think. Personally, apart from my hair becoming a bit more gray, I'm not a PhD student in Copenhagen anymore, but a Marie Sklodowska Curie Fellow at the University of Virginia and at MPE in Munich. Scientifically, plenty of progress has been made in understanding the origin of the rings and gaps in this and also in other disks, as we know from D#, for example. However, I think by focusing on the dust continuum image, we tend to forget that there are other potentially important features. When looking at the gas, for instance, we see streamers, and such streamers are most likely a consequence of infall onto the disk. In the early phase, infall is an important mechanism of replenishing the mass reservoir of disks, as demonstrated in our MHD zoom-in simulations. At later stages of evolution, we show that infall onto an existing star disk system can lead to the formation of misaligned inner and outer disk, as well as extended tail-like structures that are associated with the disk. Late infall may therefore be the origin of several observations of shadows and arcs. And if you want to know more, please watch my little presentation, scan the QR code in the lower right, and/or contact me via Slack. Let's enjoy the conference. Thanks.
Thank you very much, Michael. So next one is Rebecca Nealon.
Hi, everyone. So this is part 2 of our project looking at spirals, shadows, and precession in HD 100-453, following on from Jean-Francois's advertisement just a few posters back. Now, the main finding from part 1 was the well-defined orbit of the binary companion. In this work, in part 2, we adopt the orbit from part 1 and use this to focus on explaining the full evolution of the HD 100 system, including the misaligned inner disk. In my talk, we show that the full structure of HD 100 can be described by the schematic on the right-hand side of my poster. So starting from the outside in, we have the outer companion and outer disk shown in blue, and these were the focus of part 1. Interior to this, shown in green, we have the observed inner disk and our proposed hidden planetary companion. We constrain the likely mass and location of this hidden planetary companion using a suite of numerical simulations and synthetic channel maps like the one that we have shown on the left. And finally, with the properties of all the components of HD 100 known, the only remaining mystery was the 72-degree misalignment between the inner and outer disk. To explain this, we introduced a new model that can generate a long-lived misalignment using all the components that are shown on the right-hand side, even if the disks and planetary companion start off as coplanar. To hear our full explanation for this misalignment and the final complete picture of HD 100, you'll have to come and listen to both of our talks. Thank you.
Thank you very much, Rebecca. So next one is Tim Pierce.
Okay, hi everyone. I'm Tim Pierce, and if that name seems vaguely familiar to some of you, it's because I worked on debris disks for a number of years before leaving academia about 4 years ago. But I've since returned, and this is my first conference since coming back. So to very quickly summarize my talk on hot exozodies, we know that a significant fraction of main sequence stars appear to host very hot dust located very close to the star. But the nature of this dust is a mystery, because it should either rapidly sublimate or it should blow out the system. So what we do is we propose a new mechanism that could potentially trap dust close to the star. And that mechanism is trapping in gas. So the idea is shown on the left figure. Dust migrates in towards the star where it sublimates, releasing gas. The question then is, what happens to the subsequent dust grains that encounter this gas? Now, we show that the gas is capable of trapping dust and holding it close to the star. We show that the model can reproduce a wide range of observational constraints on hot exozodies, and in particular, it can fully reproduce the hot grain populations inferred to exist around some sun-like stars. However, for A-type stars, we find that the grains that we trap are still 5 to 10 times too large to reproduce observations. So unfortunately, the mystery of what hot exozodies actually are remains unsolved. So that's it. If you're interested, please have a look at my talk. Thank you.
Thank you very much, Tim. Next one is Isabel Rebollido. Please go ahead, Isabel.
Hi, everyone. My name is Isabel Rebollido. I'm a postdoc at Space Telescope Science Institute in Baltimore. And my talk is mainly summarizing the results of my recent ALMA observations, where I observed a sample of stars with a detected optical gas in different ways, either stable absorption arising from a circumstellar disk or variable absorptions that could come from exocometary activity. So all the objects in my sample have very bright debris disks and are distributed in the sky. There's no particular preference, but most of them are actually A-type stars. So we only have one detection on a very interesting object, which is HD 36546, that has, again, a bright debris disk, variable absorption detected corresponding to the presence of exocomets in the disk. And it also has other observations from previous works indicating there is overabundance of carbon in the system, for example, that could be pointing towards the presence of a lot of minor bodies in the system with dynamical activity. Yeah, and that's it. If you want to know more, just go check my talk and let me know if you have any questions. Thanks.
Thank you very much, Isabel. Next one is Richard Tick.
Hello, everyone. I'm Richard. I'm a SMA fellow at the CFA, Harvard, and Smithsonian. My talk is on the dynamical structures of two well-known disks, the ones around HD 163.296 and MWC 480. So this data is coming from the MAPS ALMA large program, and I think there's going to be a lot of talks throughout this conference based on that data. But my paper is specifically focused on these two bigger, brighter disks and the structures that we see in them. So in HD 163.296, we see the evidence of the outer planets that Christoph Punt detected 2 years earlier. And you can see in this residual from the rotation map that I'm plotting on the left, that the kinematic deviations we see extend over a much larger azimuthal range than we previously thought. And there's actually a tremendous amount of structure in there. In MWC 480, we also see a really stunning variety of features. In the gas velocity structure, we see rings of sort of velocity perturbations, predominantly in the vertical direction. On top of this, we also see rings in the gas temperature and tightly wound spirals. So these we both believe to be formed by a sort of Jupiter mass planet at the edge of the continuum. But there's really a whole lot of features that we need to explain here. So if you want to know about what they are and sort of hypothesize what can be making them, please come over to my channel and we can chat about that.
Thank you very much, Richard. So next speaker is Alois de Vallon.
Hello, I'm Alois, actually. I'm a PhD student at IPAG. And my talk is about the modeling of the morphology and dynamics of digital B outflows with ALMA. And actually, digital B is a nice class 1 protostars with a lot of interesting features. For example, a large unstructured disk with infall and also a nested rotating outflow. So I don't think I need to talk to you about how having structure in disk is interesting, especially not on this conference. But what I'm more interested in is in the outflow, because it can extract angular momentum and also extract mass. So in my talk, I'm doing a little bit of presentation about digital B, and I also present analytical tools to study the outflows and to characterize the outflows. All of that to discuss about more interesting questions like the origin of the outflow and also the anchoring radius of the outflows, and also what is the impact of this outflow on the disk in terms of evolution of the star and also evolution of planetary formation. Thank you.
Thank you very much, Alois, and sorry for the mispronunciation. This is what happens when you try to fake French accent. So next is Apostolos Zormpas, who's going to talk first about his talk and then about his poster, I believe.
Yeah, hi. Hello, everyone. I'm Apostolos Zormpas, and I'm a PhD student working at the LMU in Munich. And I'm going to present here a summary of a work that we are doing with Till Bürstel in Munich and Giovanni Rosotti in Leiden. So we performed a disk population synthesis of 100,000 models of gas and dust disk evolution, where we varied key parameters of the initial conditions. We calculate the luminosity and the effective radius for all models, and we simulate two different cases, one where we have a smooth surface density profile and one where we include planets in different locations and with different masses. By selecting only the disks that lie on the size-luminosity relation, the observed size-luminosity relation from Tripathi et al. 2017, we managed to constrain the parameter range and search for trends between the initial conditions and the disks that stay on the size-luminosity relation for all their lifetime. So we find that we need to form substructures fast enough in order to maintain more disks on the size-luminosity relation. We found how the position of the planet affects the disks on how they evolve on the size-luminosity relation, and we also observe a trend towards low alpha values and high disk masses. Of course, there are many more conclusions that are presented in the talk, and more initial conditions that we change. We also use some neural networks. So I hope you find it interesting. And if you have any questions, feel free to ask me via Slack or via email.
And then the next one.
Yeah, so it's me again. Hi. So I have another work to present, and I will talk about an already published paper here with Giovanni Picogna and Barbara Colano in Munich and Willy Klei in Tübingen. And here what we did is that we had 3D radiation hydrodynamical models of very high resolution, where we measure the solid accretion rate efficiency on different planetary cores of 5, 10, and 100 Earth masses. What we find is that when we use a realistic equation of state and radiation, the disk at 5 AU is able to efficiently cool down and consequently reduce its aspect ratio. So this leads to the result that where the pebble isolation mass is reached before the core grows to 10 Earth masses, and as you can see here in the right plot, the reduced isolation mass, compared to the literature, of course, has two major implications. One is that the super-Earth planets are able to open a gap at 5 AU where we located the planet. And the other one is that the core doesn't reach the critical mass for runaway gas accretion, leading to another barrier to giant planet formation. But on the other hand, it could explain the large abundance of super-Earth planets in the observed population. For more details, you can read the poster, or you can read the paper if you scan the QR code here, and you can ask me via Slack or via email again. Thank you very much.
Thank you very much, and thank you to all of you for presenting or summarizing in such a very short time your work. If any one of the attendees is interested in any of these posters and talks, please go ahead. Look for the name of these presenters in the Slack channel, and you're going to be able to join their personal channel, and you're going to be able to find their links to their contributions there. I think that's everything for today. Thank you very much for all the speakers. To all the speakers, thank you very much to Joanna Gita for chairing this session. And hopefully everything is going to go as smooth as tomorrow. See you everyone tomorrow, same time, same place. Well, not same place because the link is going to change. We're going to send the link again around 30 minutes before the session starts. Thank you. Bye.